Welcome to Night Cosmos Sleep. In the direction of the constellation Sagittarius, about 47 light-years from Earth, lies an object so faint that it is nearly invisible, known as W1935. It does not orbit a sun-like star, receives no intense light from outside, and retains only the internal heat it is slowly losing. Under normal expectations, a world like this should gradually cool and grow quiet in the darkness. But data from the James Webb Space Telescope reveals something entirely different. When scientists analyzed the faint light coming from W1935, they discovered that methane in its atmosphere was emitting infrared radiation. Methane itself is not especially unusual, since the molecule also exists on many giant planets and can form without life. What is difficult to explain is its glowing state, because it suggests that part of the atmosphere is receiving an additional source of energy. Models also indicate that the upper atmosphere of W1935 may be warmer than expected, but without a host star to provide light and stellar wind, where could that energy be coming from? Heat may be rising from deep within the object, or a powerful magnetic field may be capturing charged particles and guiding them down into the atmosphere. Another possibility is that W1935 is producing auroras, though not the kind of visible glow we see on Earth. They may appear only in infrared wavelengths, and the process itself could be causing the methane to shine. Scientists have also proposed that a small nearby object might be supplying material to the magnetic field, much as the Moon Io helps generate auroras on Jupiter. New observations suggest that W1935 may not be entirely alone. The point of light, once thought to be a single object, now appears to contain two cold components positioned close together, raising new possibilities involving magnetic interactions or sources of material that have not yet been detected. Even so, scientists still do not know which component is producing the unusual methane signal. James Webb has observed the glowing methane, while atmospheric models suggest that the upper layers may be heating up. But auroras, magnetic fields, internal energy, and the influence of a companion object remain hypotheses that are still being tested. The mystery of W1935, then, is not whether life exists there. The real question is what is supplying energy to the atmosphere of a world without a Sunday. Before we can find the answer, we first need to understand what W1935 truly is. A star that never managed to shine, a wandering giant planet, or a world suspended somewhere between the two. Some celestial objects are born much like stars, yet never grow massive enough to truly become one. They do not blaze brightly in space, nor do they have a clearly defined surface like rocky planets. Instead, they quietly cool in the darkness, carrying clouds, storms, and powerful magnetic fields much like those of giant planets. W1935 is one of the worlds that exists along this indistinct boundary. A star like the Sun begins as a vast cloud of gas and dust, collapsing under the force of gravity. As more material gathers, the core becomes increasingly compressed, causing its temperature and pressure to rise. Once the core grows hot enough, nuclear reactions begin, releasing an enormous amount of energy. This is the source that allows a star to shine steadily for billions of years. Brown dwarfs can also form from collapsing clouds of gas in much the same way. But they do not contain enough material to create a core as hot and stable as the one inside the Sunday. They may undergo certain reactions during their early stages, but they cannot sustain their glow over long periods. As their initial energy fades, these objects gradually begin to cool. For this reason, brown dwarfs are often described as worlds that lie somewhere between stars and planets. They resemble stars in the way they form, since many brown dwarfs emerge independently from clouds of gas in space. Yet in appearance, temperature, and atmospheric structure, they are more like planets. These blurred boundaries make it difficult to describe them accurately as either stars or planets. The name brown dwarf can also be misleading. These objects would not necessarily appear brown if humans could see them directly. Most are far too faint to emit much light within the range visible to the human eye. Instead, they release most of their heat as infrared radiation, much like a warm object that continues to give off energy even though it does not visibly glow in the dark. Some brown dwarfs have masses dozens of times greater than Jupiter's. Their diameters, however, are usually not much larger than Jupiter's. This is because as their mass increases, gravity also becomes stronger, compressing the material inside more tightly. A heavier brown dwarf does not necessarily expand in size. Instead, it may simply become denser. If a brown dwarf were placed beside Jupiter, the two might appear nearly identical in size. But inside the brown dwarf, matter would be compressed under far greater pressure. Gravity on these objects is also much stronger, holding their atmospheres tightly and creating conditions unlike anything humans could experience on Earth. W1935 belongs to one of the coldest classes of brown dwarfs ever discovered. Here, the word cold only makes sense in comparison with stars, because its temperature is still far higher than the environments familiar to human life. While the sun's surface reaches thousands of degrees, W1935 has a temperature of only a few hundred degrees Celsius. By stellar standards, it is a cool world. Its low temperature means that W1935 emits very little visible light. Even if humans could observe it from nearby, the object would probably still appear extremely dark. Most of the energy escaping from it lies in the infrared, beyond the reach of human vision. Only telescopes designed to collect infrared light can clearly detect and study a world like this. But being cold and faint does not mean being completely still. W1935 still contains heat left over from its formation and from the continuing contraction of its material. That heat keeps escaping outward, driving movement within the atmosphere. Warmer gases may rise while cooler material sinks, creating vast circulation patterns around the object. The atmosphere of a brown dwarf may contain clouds very different from those on Earth. On hotter brown dwarfs, clouds can form from condensed particles of minerals or metals. As the object cools, clouds of water and more familiar compounds may begin to appear. The composition and thickness of these clouds vary with the temperature of each atmospheric layer. On W1935, molecules such as water vapor, methane, and ammonia may exist in the atmosphere. These substances are also found on the giant planets of our solar system. This similarity is why scientists often use Jupiter and Saturn as points of comparison when studying W1935. Even so, there are important differences between them. Jupiter and Saturn formed within the disk of material surrounding the Sunday. They have always been influenced by sunlight, the solar wind, and the gravity of their central star. W1935, by contrast, formed as an independent object and does not orbit a bright star. It has a planet-like atmosphere, yet an origin more closely resembling that of a star that never fully began to shine. If we could travel close to W1935, we would not find solid ground on which to land. From the outside, a spacecraft would first pass through thin upper layers of atmosphere. As it descended, the gas would grow denser, the pressure would increase, and the temperature would continue to rise. There would be no clear boundary marking where the atmosphere ended and the interior began. On Earth, we can point to the ground and call it the planet's surface. On W1935, the idea of a surface is not so simple. Its outer gases gradually transition into denser states under immense pressure. Any instrument attempting to descend would be destroyed by heat and pressure long before reaching the deepest regions. Even without a solid surface, W1935 may still have weather. Winds could move around the object, clouds could shift, and bright or dark regions might appear as it rotates. Some brown dwarfs have been observed to change in brightness over time, suggesting that their atmospheres are uneven and may contain bands of clouds or enormous storms. Rapid rotation could also produce powerful wind systems. When an object completes a full rotation in only a few hours, its atmosphere is carried along, forming bands of motion around it. These currents transport heat from one region to another, turning the atmosphere into a constantly changing system rather than a motionless layer of gas. Brown dwarfs may also possess strong magnetic fields. Although they are not true stars, the movement of electrically conductive material deep inside them can still generate magnetism. Some brown dwarfs emit repeating radio pulses. which are considered signs of magnetic activity. This raises the possibility that these dark, cold objects may also produce auroras. This is where comparisons with Jupiter and Saturn become especially important. Both giant planets have magnetic fields, deep cloud layers, powerful winds, and auroras near their poles. W1935 may share many of these features, but it receives no energy from a nearby star. If auroras exist in its atmosphere, the particles and energy that create them must be supplied through a different mechanism. This makes W1935 a remarkable natural laboratory. It allows scientists to observe a planet-like atmosphere that is almost entirely free from the influence of a host star's light. The phenomena found there may reveal how an atmosphere operates when its main sources of energy come only from within the object or from the surrounding environment of space. W1935, then, is more than a star that failed to shine, nor is it simply a larger version of Jupiter. It belongs to a distinct kind of world, where the characteristics of stars and planets exist together. That combination has produced an atmosphere familiar enough for us to recognize methane, yet different enough for the methane to behave in a way that remains unexplained. If W1935 formed much like a star, why does its atmosphere display so many features resembling Jupiter and Saturn? And if this object is too faint for human eyes to see, how were scientists able to find it among the countless points of light scattered across the sky? To understand the unusual methane signal, we must return to the moment when W1935 was first recognized. Its story did not begin with a clear image, but with an exceptionally faint infrared point slowly moving against the background of the sky. W1935 was not discovered because it stood out brightly in the sky. It was recognized as a very faint infrared point, quietly shifting across the background stars and images taken at different times. In the light visible to human eyes, the object nearly disappears altogether. It was this subtle motion that allowed scientists to realize that a world was drifting through the darkness, much closer to us than most of the stars behind it. Cold brown dwarfs like W1935 are among the most difficult celestial objects to detect. They do not shine brightly like stars because they lack an internal energy source powerful enough to sustain their light for billions of years. Nor do they orbit a luminous star whose light they can reflect, as familiar planets do. As a result, against a sky filled with countless points of light, W1935 leaves almost no trace at ordinary visible wavelengths. Yet an object does not need to shine visibly in order to give off heat. The human body, a rock warmed by the sun, or a planet hidden in darkness all emit energy in ways the naked eye cannot see. W1935 does the same. Although it is gradually cooling, it remains far warmer than the surrounding space and continues to release a faint infrared glow. Infrared light lies beyond the red edge of the spectrum visible to human eyes. We cannot see it directly, but specialized instruments can collect the signal and convert it into data. For dark objects like W1935, infrared is almost the only doorway through which we can know they exist. Rather than searching for visible light, astronomers search for the heat that remains. The difficulty is that the infrared sky is far from empty. Interstellar dust, extremely distant galaxies, and many other cold objects can all produce signals of their own. A faint point appearing in an image is not enough to prove that it is a brown dwarf. Scientists must determine whether it moves, what its infrared colors look like, and whether the signal appears again in later observations. For this reason, the same region of sky is photographed repeatedly. When the images are placed side by side, most distant stars remain almost perfectly fixed, but an object closer to the solar system shifts slightly against the background stars behind it. The change may be extremely small, yet when the images are rapidly alternated, the faint point appears to move slowly across the sky. This is how many cold brown dwarfs are discovered. They do not announce themselves with a powerful burst of light, but with a quiet and subtle motion. In any single frame, an infrared point may look completely ordinary. Only when time is added to the data does the object reveal that it does not belong to the distant, motionless background. W1935 was identified with the help of Backyard Worlds, a citizen science project that allows large numbers of people to participate in the search for cold worlds near the solar system. Participants examine sequences of infrared images and look for points of light that move in unusual ways. The task may seem simple, but it can be remarkably useful, because the human eye is sometimes better than automated systems at recognizing motion within images. Across the immense volume of data, participants can mark noteworthy points for scientists to examine more closely. Most signals may later prove to be noise, a variable star, or an unrelated artifact. But occasionally, a tiny point of light is a genuine celestial object that has never been fully studied. W1935 was one of the worlds brought out of the darkness in this way. Detecting motion was only the first step. To determine the nature of W1935, scientists had to observe its infrared colors and compare them with those of known brown dwarfs. A cold object does not emit energy evenly across every wavelength. Its atmosphere absorbs some portions of the light more strongly than others, creating a distinctive signal that can be used to estimate its temperature and composition. From the earliest observations, W1935 was classified as an extremely cold brown dwarf. It is close enough to study, yet still too faint for older telescopes to easily separate every detail within its light. Instruments that came before James Webb could confirm that the object existed and reveal some of its general characteristics. But the true story hidden within its atmosphere remained concealed by the weakness of the signal. W1935 lies about 47 light-years from Earth. That number may not sound especially large compared with the scale of the galaxy, but the actual distance is still far beyond any journey humanity has ever made. Light travels at nearly 300,000 kilometers per second, and yet it still takes 47 years to cross the distance from W1935 to telescopes near Earth. This means we do not see W1935 as it exists at this very moment. The photons collected by James Webb left the object nearly half a century ago, then crossed interstellar space before finally reaching the solar system. Every piece of information about its clouds, temperature, or methane is an old message that began its journey 47 years in the past. In everyday life, light arrives so quickly that we tend to believe we are seeing everything instantly. But in astronomy, looking across great distances also means looking into the past. The sun we see is already more than 8 minutes old. The W1935, captured in James Webb's data, is an image of a world from nearly half a century ago. That distance also prevents W1935 from appearing as a clearly defined sphere. Even to James Webb, it initially remains little more than a tiny point of light. The telescope cannot see individual clouds, follow separate storms, or photograph a visible horizon. Yet a single point of light can contain far more information than its appearance suggests. Every ray of light escaping W1935's atmosphere passed through different layers of gas before reaching us. Along the way, some portions were absorbed by molecules, while others continued outward into space. When the signal is separated into individual wavelength regions, those areas of missing and excess light begin to appear. This is when a point of light starts to tell the story of an atmosphere. James Webb was designed to observe the universe in infrared wavelengths with extraordinary sensitivity. Its large mirror allows it to collect more light from faint objects, while the instruments behind it can divide that signal into much smaller components. For W1935, this ability is more important than producing a beautiful image. The telescope must gather enough light to read the traces left by individual molecules. White light can be imagined as a piece of music composed of many different notes. When we hear everything at once, we only know that a melody is playing. But when each note is separated, the finer details begin to emerge. A spectrum works in much the same way, except that what is being separated is not sound, but the individual wavelengths of light. Each molecule interacts with light in its own distinctive way. Water vapor leaves traces in certain regions, methane in others, while ammonia and carbon dioxide have signatures of their own. These patterns are not as clear as written words, but after years of laboratory research and planetary observations, scientists have learned how to recognize them. When a molecule absorbs light, it leaves a darker region in the spectrum. When a layer of gas receives enough energy and emits light in return, that same region may appear brighter than expected. By comparing the data with atmospheric models, researchers can infer which substances are present and how temperature changes between different layers. This is why James Webb does not need to see the surface of W1935. From only a tiny amount of light, the telescope can still reveal that the object is not a completely dark sphere. Hidden within that point is a thick atmosphere containing water vapor, methane, and many other molecules. Each substance has left its own trace as the light traveled outward into space. Of course, reading a spectrum is not as simple as looking at a single feature and naming a molecule. Many signatures may overlap. While clouds and temperature can alter the signal, scientists must test numerous models to determine which atmospheric structure can reproduce the light observed by James Webb. Every conclusion, therefore, comes with a certain degree of uncertainty. W1935 was selected as part of an observing program focused on several cold brown dwarfs. The goal was not only to study one object in isolation, but also to compare it with others that had similar temperatures and characteristics. When many worlds are observed with the same instrument, unusual differences become easier to recognize. A signal may be difficult to identify without a suitable object for comparison. Among that group was another brown dwarf known as W2220. The two objects are similar in temperature and in many features of their light. At first glance, they could be considered two worlds belonging to the same class, cooled to comparable levels and containing many of the same molecules in their atmospheres. It was precisely this similarity that made the difference between them so important. Across most of their spectra, W1935 and W2220 do not show a dramatic contrast. Both display the signatures of cold, hydrogen-rich atmospheres containing water vapor, methane, ammonia, and several carbon-bearing compounds. Scientists could begin studying them with the same general set of models, but when they reached the wavelengths associated with methane, the resemblance suddenly ended. On W2220, methane behaves in the familiar way. It absorbs some of the light rising from deeper layers and leaves a dark signature in the spectrum. This is what models of cold atmospheres usually predict. The upper atmosphere is cooler, and as light passes through it, methane captures certain wavelengths before the remaining light escapes into space. On W1935, however, methane produces the opposite signal. Instead of missing light, the data show additional light appearing at wavelengths characteristic of the molecule. The difference is not that one world contains methane while the other does not. Both atmospheres contain methane, but the molecule is behaving in two entirely different ways. This comparison reduces the likelihood that the signal is merely an ordinary instrumental error. The two objects were observed as part of the same program, yet they produced different results. If methane is glowing on W1935, then its atmosphere must contain a condition that is absent from W2220, or at least not present there to the same degree. Perhaps the temperature of one atmospheric layer is rising instead of continuing to fall. Charged particles may be entering a magnetic field and transferring energy to the gas. It is also possible that motions deep within the object are carrying heat upward. The initial data do not reveal which mechanism is correct, but they do show that W1935 is not an entirely ordinary cold brown dwarf. From a faint infrared point moving against the background sky, W1935 has become a mystery centered on the source of its energy. The search did not end when the object was discovered. On the contrary, it was only when James Webb separated its light into a spectrum that the greatest question emerged. Why would two nearly identical worlds cause the same molecule to behave in opposite ways? On W2220, methane removes some of the light and leaves behind the familiar signature of absorption. On W1935, methane appears to be returning light to space. To understand this contrast, we must look more deeply into the spectrum and determine what is supplying energy to this unusual layer of gas. If two rooms have the same temperature, the same kind of air, and nearly identical conditions, yet only one gives off a strange color of light, the most important question is not how beautiful that color appears. The deeper question is how energy entered the room in the first place. This is also what scientists began asking when they compared W1935 with another brown dwarf known as W2220. From a distance, the two objects look similar enough to serve as a natural control pair. Both belong to an extremely cold class of brown dwarfs, have comparable brightness, and emit most of their energy in the infrared. Their atmospheres also contain many of the same molecules, including water vapor, ammonia, methane, and carbon-bearing compounds. That similarity is especially important. If W1935 had been observed alone, its unusual signal might have been dismissed as an error, noise in the data, or a difficult detail within the models. But when it is placed beside W2220, the difference becomes unmistakable. Two nearly identical worlds cause the same molecule to behave in opposite ways. On W2220, methane does what scientists normally expect it to do in a cold atmosphere. Light rises from deeper, warmer layers and then passes through the atmosphere above. Methane captures some of that energy at specific wavelengths, leaving darker regions in the spectrum. The process can be imagined as looking at a light bulb through a sheet of colored glass. The bulb still produces many colors of light, but the glass allows some colors to pass through while holding back others. When the light is measured on the far side, certain portions are missing. This is the signature of absorption. Within the atmosphere of a celestial object, each type of molecule absorbs a different range of light. Methane has its own signature, water vapor leaves another, and ammonia produces a distinct pattern of its own. By studying these missing regions, scientists can determine what a distant atmosphere contains without ever collecting a physical sample. On W2220, the methane signature appears in exactly this familiar way. It removes some of the infrared light and leaves behind a relatively ordinary absorption feature. The result fits the picture of an atmosphere that grows cooler with altitude from the deeper layers toward the upper regions. There is nothing especially unusual about the way methane interacts with the light, but on W1935, at the very wavelengths where methane should be absorbing energy, James Webb detected an increase instead. Rather than creating a region of missing light, the methane appears to add light to the spectrum. It is not merely standing in the path of the radiation, it is releasing energy back into space. This is known as emission. A molecule receives energy from its surroundings, enters a more energetic state, and then releases that energy in the form of light. It can be compared to an object being heated. Once it has absorbed enough energy, it begins radiating energy that was not present before. The methane in W1935's atmosphere does not glow like a flame visible to the human eye. Its light lies in the infrared, entirely beyond the range of human vision. James Webb did not photograph a clearly defined band of color surrounding the object. Instead, it measured an increase in brightness at wavelengths specifically associated with methane. It is much like hearing a note that sounds higher than expected within an extremely faint piece of music. No one can see where the sound is coming from, but a sensitive enough instrument can still detect that the note is there. And when it appears at precisely the position associated with methane, scientists know that this molecule is involved in the unusual phenomenon. Methane itself is not rare on cold worlds. It exists in the atmospheres of Jupiter, Saturn, Uranus, Neptune, and many other celestial objects. When temperatures fall low enough, methane can remain stable in large quantities within a hydrogen-rich atmosphere. Its presence on W1935 is therefore not surprising. What is unusual is the condition of the atmospheric layer containing it. For methane to produce emission, that layer must be warmer or more strongly energized than simple models predict. Some source of energy has entered the atmosphere, affected the molecules, and caused them to release infrared light. If W1935 were powered only by internal heat slowly escaping outward, its temperature would normally be expected to decrease with altitude. The deeper layers are more strongly compressed and therefore warmer, while the upper layers are thinner and colder. Under those conditions, methane high in the atmosphere should absorb light just as it does on W2220. But the data suggests that an upper layer of W1935's atmosphere may be warmer than expected. As light passes through this region, methane does not simply remove energy from it. Instead, the gas may be adding energy at its characteristic wavelengths. This indicates that the temperature structure of W1935 is more complicated than that of a world merely cooling with time. The difference between the two brown dwarfs therefore becomes the key to the entire story. W2220 reveals the ordinary state that scientists can use as a point of reference. W1935 shows what may happen when an additional energy source appears high in the atmosphere. Because the two worlds are so similar, many overly simple explanations can be ruled out. For example, if methane emission were caused only by the overall temperature of a brown dwarf, W2220 should produce a similar signal. If it were a natural feature of every cold atmosphere, other objects in the observing program should show the same result. Yet the prominent signal appears only on W1935. This does not mean that W1935 is completely unlike other brown dwarfs. Most of its atmosphere still displays familiar characteristics. Water vapor, ammonia, and carbon-bearing molecules all remain visible in the spectrum. Only within certain regions does the light suggest that the atmospheric structure has been altered by an additional process. That process may be occurring only within a thin layer high in the atmosphere. It could also be concentrated in a particular region, perhaps near the magnetic poles. Because W1935 is so distant and appears only as a point of light, James Webb cannot yet reveal where the emission is located. The telescope records only the combined light coming from the entire object. If the methane is glowing around the polar regions, the signal may be connected to auroras. If the emission extends across the atmosphere, energy may be rising from deep within the object. And if the signal changes as W1935 rotates, a hot region or a vast weather system may be moving into and out of view. But during the initial observations, scientists did not have enough data to distinguish among these possibilities. They knew only that W1935 did not follow a simple temperature structure. A region that should have grown colder with altitude instead contained a layer of gas energetic enough to make methane emit light. This is also where the methane signal can easily be misunderstood. Because methane is often discussed in searches for life beyond Earth, some might assume that W1935 carries a biological signature. But in the hot, dense, hydrogen-rich atmosphere of a brown dwarf, methane can be produced entirely through natural chemistry. There is no evidence that living organisms are creating this gas. In fact, the environment of W1935 is profoundly different from Earth. It has no clearly defined solid surface, no exposed oceans, and no steady illumination from a nearby star. Temperatures throughout its atmospheric layers also lie far beyond the conditions familiar to human life. What James Webb detected, therefore, is not a gas of life in any direct sense. The signal shows that methane is being heated or energized by an unknown mechanism. This is a question about atmospheric physics and energy, not evidence of extraterrestrial organisms. Making that distinction only strengthens the discovery. Science does not need to turn W1935 into a living world to make it fascinating. The presence of a glowing atmospheric layer on an object without a host star is enough to pose a major mystery. That source of energy must exist somewhere, even though it cannot yet be seen directly. One possibility is that W1935 has a powerful magnetic field. Trapped charged particles may plunge into the atmosphere and transfer energy to the methane. The process would resemble auroras on giant planets. Although the source of the particles around W1935 remains unclear. Another possibility is that energy from deep within the object is being carried upward by motions in the atmosphere. W1935 is still extremely hot in its deeper layers. Rising currents, atmospheric waves, or enormous storms may transport some of that heat upward, creating an unusually warm region high above. It is also possible that another celestial body is influencing W1935. If a moon or companion object is supplying material nearby, the magnetic field could capture those particles and produce powerful streams of energy. When the methane signal was first discovered, however, this possibility remained only a hypothesis. No explanation can be chosen, simply because it sounds plausible. Scientists must search for additional evidence to test each possibility. Auroras may be accompanied by radio signals. Energy rising from within may produce widespread changes across the atmosphere. A companion object could cause the signal to vary with orbital motion. Before moving on to those tests, however, researchers first needed to understand what kind of temperature structure could produce the observed spectrum. The James Webb data were entered into models in which many different atmospheric arrangements were tested. Some allowed the temperature to decrease steadily with altitude, while others added a warmer layer higher in the atmosphere. The results showed that a conventional model could not adequately explain the methane emission. To produce the amount of light that had been measured, W1935's atmosphere required a region where the temperature no longer continued to fall. There, the pattern appeared to reverse. As the gas rose higher, it began to grow warmer. This is what separates W1935 from its nearly identical counterpart. The two objects may contain similar molecules, but their temperature structures are not the same. On W2220, methane absorbs light within a cold atmospheric layer. On W1935, methane glows inside a region receiving an additional supply of energy. From a subtle difference in the spectrum, scientists traced the signal to an unusual atmospheric layer. Yet that discovery opened an even larger question. Without a star shining on it from outside, what could be heating the upper atmosphere of W1935? As we move higher through the atmosphere of this world, the temperature does not appear to keep falling. At a certain altitude, it begins to rise again. On Earth today, most methane in the atmosphere is connected either directly or indirectly to life. Microorganisms in wetlands, the decomposition of organic matter, and the digestive systems of certain animals all produce this gas. For that reason, whenever methane is detected on a distant world, the question of life tends to arise almost immediately. But a single molecule cannot tell the complete story of an entire world. Methane can be produced by living organisms, yet it can also form through interactions among rock, water, heat, and chemical reactions that require no living cells at all. To understand what it means, scientists must consider where the molecule appears and under what conditions. Methane is made of carbon and hydrogen. In Earth's atmosphere, it exists only in small amounts, but it has a powerful ability to trap heat. Sunlight and chemical reactions gradually break the molecule apart, so methane cannot remain indefinitely unless some source continues to replace it. This is why methane draws attention in the search for life. If it is constantly being destroyed yet remains present in large quantities, some process must be producing it. On an Earth-like planet, that source could be biological activity, geological processes, or a combination of several mechanisms. In oxygen-poor wetlands, microorganisms break down organic matter and release methane. The gas also appears in sediments, animal digestive systems, and certain environments deep below the ground. Agriculture, fuel extraction, and leaks of natural gas add even more methane to the atmosphere. Its clear connection with living organisms is why methane is often described as a potential biosignature. If it were found on a rocky planet with moderate temperatures, liquid water, and an atmosphere similar to Earth's, the signal would be well worth investigating. But something being worthy of investigation does not mean the evidence has already been confirmed. A world containing methane does not necessarily contain life. Scientists must also determine how much of the gas is present, how long it survives, and whether natural processes could produce it. The molecules found alongside methane are equally important because they reveal the direction in which the surrounding chemistry is operating. There is no single miracle gas that can automatically confirm extraterrestrial life. The meaning of any molecule depends on temperature, pressure, atmospheric composition, the type of celestial object, and the surrounding sources of energy. The same signal can mean very different things when it appears on a rocky planet rather than a giant gaseous world. This can be compared to seeing water vapor. In a kitchen, it may come from a boiling pot. Near a volcano, the same vapor may be produced by heat and geological activity. Similar traces do not necessarily come from similar sources. Within the solar system, methane appears in many places where there is no evidence of life. Jupiter and Saturn both contain the molecule in their atmospheres, even though most of their material consists of hydrogen and helium. There, methane is a natural product of atmospheric chemistry rather than a sign of living organisms. Uranus and Neptune also contain methane. The molecule absorbs some red light, helping create the distinctive blue coloring of both planets. Yet no one considers that color evidence that life is active beneath their deep, cold cloud layers. Titan, Saturn's largest moon, even has lakes and seas of liquid methane on its surface. Its atmosphere contains many carbon compounds and supports an extremely complex weather system. Even so, the abundant presence of methane is still not enough to prove that living organisms exist there. Methane can also form deep inside a celestial body, where hot water reacts with rock. Certain minerals release hydrogen, which can then combine with carbon to produce methane. This entire process can occur without any biological activity. Volcanic activity may carry gases from the deep interior into the atmosphere. Fractures can also release methane that has remained trapped since the object first formed. If a world remains geologically active, this gas could continue to be replenished for millions or even billions of years. Large impacts can also alter the composition of an atmosphere. A carbon-rich asteroid striking at high speed would generate heat and drive many new chemical reactions. Under certain conditions, this process could produce methane or related compounds. Light from a star can also break molecules apart and recombine their components along different chemical pathways. Depending on the temperature and initial composition of the atmosphere, methane may form entirely through natural chemistry. Detecting it, therefore, is only the beginning of the investigation. When we return to W1935, this caution becomes even more important. It is not a rocky planet orbiting within a temperate region around a sun-like star. It is a brown dwarf with a thick, hot, hydrogen-rich atmosphere and no clearly defined solid surface like Earth's. The deeper we descend, the more sharply the pressure and temperature rise. There are no surface oceans, continents, or familiar environments in which life on Earth developed. Methane under these conditions cannot be interpreted in the same way as methane on a temperate rocky planet. In fact, models of cold brown dwarfs have long predicted that methane can exist in their atmospheres. As temperatures fall, carbon is more likely to appear in the form of methane. Its detection, therefore, was not what surprised scientists most. If James Webb had observed methane absorbing light in the ordinary way, the result would have matched expectations. What was unusual was that, within a particular region of the infrared spectrum, the signal appeared stronger than it should have been. The molecule seemed to be emitting light, rather than simply removing some of the light passing through it. A molecule does not begin glowing on its own without receiving energy. It must be heated, struck through collisions, or excited by some other mechanism. Only after absorbing energy can methane release part of it again, as the infrared light detected by James Webb, calling methane a gas of life in this case, could therefore send the story in the wrong direction. The mystery is not whether organisms are producing the gas. What must be explained is the source of energy acting upon the atmospheric layer that contains it. The molecule can be imagined as a light bulb. Seeing the bulb glow does not reveal where the electricity is coming from. To understand the entire system, we must trace the wiring, locate the source, and identify the mechanism that delivered energy to that particular place. If the atmosphere received heat only from the deeper layers below, the temperature would normally decrease with altitude. The colder upper layers would absorb some of the light and create an absorption signature. This is the kind of signal observed on many other brown dwarfs. But on the world being studied, methane produces an emission signal instead. This suggests that at least part of the upper atmosphere may be warmer than predicted. An additional source of energy appears to be operating in a region that should be colder than the layers beneath it. That energy may be rising from within. Powerful currents, storms, or waves moving through the atmosphere could transport heat from the deep interior to higher altitudes. As these motions weaken, their energy may be converted into heat, warming a particular layer of gas. Another possibility involves a magnetic field. If this brown dwarf possesses a powerful magnetic field, it could capture charged particles from the surrounding environment. Those particles might then be guided down into the atmosphere, where they collide with methane and other molecules and release energy. This mechanism would be similar to the way auroras form on Earth, Jupiter, and Saturn. However, this world has no host star supplying a strong stream of stellar wind. If auroras are truly occurring there, the source of the charged particles remains a major part of the mystery. A small nearby object could be supplying the material. If such an object releases gas or dust into space, the magnetic field could capture it and create streams of particles moving around the system. As those particles fall into the atmosphere, they could heat the upper layers and cause the methane to glow. This possibility brings to mind Io, Jupiter's volcanic moon. Io continuously releases material into space, providing a major source of particles for Jupiter's magnetic field. Those particles help sustain the planet's powerful auroral regions, even though Io itself is far smaller than Jupiter. Even so, there is not yet enough evidence to confirm that a similar mechanism is operating here. The source of the particles, the strength of the magnetic field, and the precise location of the emitting region have not been determined. James Webb has revealed only the final result. Methane is producing more light than expected. There may also be another process that current models do not yet describe fully. Brown dwarfs occupy the boundary between stars and planets, so their atmospheres may contain mechanisms that have never been clearly observed within the solar system. The present signal may be the first time such a process has emerged clearly enough to be studied. This is why it is important to separate what has been observed from what remains speculative. The most certain result is that methane is producing an infrared emission signal. The warming of an atmospheric layer is an inference drawn from models. Auroras, magnetic fields, and companion objects remain hypotheses that require further evidence. If these different levels of information are blended together, an atmospheric discovery can quickly be transformed into a story about extraterrestrial life. But when they are kept separate, the true mystery becomes clearer. A world without a host star is receiving energy through a mechanism that cannot yet be fully explained. Setting aside the possibility of life does not make the story any less compelling. On the contrary, it brings us back to the question the data are actually asking. How can an object powered only by its remaining internal heat create a warm layer high in its atmosphere? If the energy is rising from the deeper layers, what mechanism carries it upward? If charged particles are plunging into the atmosphere, how powerful must the magnetic field be? And if auroras truly exist, what source of material is sustaining them in a system without the familiar flow of stellar wind? To answer these questions, scientists must reconstruct how the temperature changes from the deep atmosphere to the upper layers. That structure determines whether methane absorbs light or emits it. And it is here that the models reveal a result that runs against ordinary intuition. In a simple atmosphere, the temperature should decrease as the gas moves farther from the hotter regions below. But on this object, that pattern does not appear to continue indefinitely. At a certain altitude, the upper atmosphere begins to warm instead of growing colder. Methane, then, is not the answer to the mystery. It is only the trace leading us toward an atmospheric region being heated by an unseen source of energy. To understand that source, we must enter a phenomenon in which temperature behaves in the opposite way from what is normally expected. The higher we rise, the atmosphere does not continue to grow colder. At a certain layer, the temperature begins to increase once again. Normally, the farther we move from the hot layers below, the more the temperature decreases. On a planet or brown dwarf, the deep interior retains more heat, while the upper atmosphere becomes thinner and colder. But that pattern does not always continue indefinitely. In some cases, the atmosphere unexpectedly begins to warm again at higher altitudes. This phenomenon is known as a temperature inversion. Instead of continuing to cool with altitude, an upper layer receives additional energy and becomes warmer than the region directly beneath it. This may seem counterintuitive, but it is not entirely unfamiliar. Even within the solar system, many worlds have atmospheric layers that behave in a similar way. On Earth, the temperature gradually decreases as we rise above the surface, through the lower atmosphere. At greater altitudes, however, a layer containing ozone absorbs energy from sunlight. As a result, the temperature begins to rise again. Even as the atmosphere extends farther from the ground, an external source of energy has altered the usual pattern. This shows that an atmospheric layer can warm if it receives enough energy. That energy may come from light, charged particles, electrical currents, or powerful motions within the atmosphere. The important question is not where the heat is located, but what mechanism is delivering energy to that region. On Jupiter and Saturn, the story is even more complicated. These giant planets receive sunlight, but that energy alone is not enough to explain all the high temperatures found in their upper atmospheres. Scientists have therefore had to search for additional sources, ranging from atmospheric waves to auroral activity around the polar regions. Large storms can generate waves that travel upward. As these waves pass through different layers of gas and gradually dissipate, their energy is converted into heat. The process is much like ripples carrying energy far from the place where they formed before releasing what remains in another region. Electrical currents within a magnetic field can also heat an atmosphere. When charged particles are guided down toward the poles, they collide with gas molecules and transfer energy to their surroundings. Some of that energy becomes auroral light, while the rest raises the temperature of the upper atmosphere. Thanks to these examples within the solar system, the idea of an atmosphere warming with altitude is not too difficult to imagine. But the object being studied presents a much greater problem. It does not orbit a bright star like the Sun, so the familiar energy supplied by nearby starlight is almost entirely absent. It still retains heat from its formation and continues releasing that energy into space. But internal heat would normally travel outward from the deeper layers through a relatively steady process. Without an additional mechanism, the atmosphere would still be expected to grow colder with altitude. The James Webb data reveal a different picture. Methane in one part of the atmosphere is not merely absorbing light, but emitting additional energy in the infrared. To produce such a signal, the methane-bearing layer must be warmer or more strongly energized than standard models predict. Scientists cannot send an instrument there to measure the temperature directly. At a distance of nearly 47 light-years, any visit by present-day spacecraft is entirely impossible. Instead, they must use light as an indirect thermometer and reconstruct the atmosphere from the traces preserved in its spectrum. Each model begins with a different temperature structure. In some, the temperature decreases steadily from the deeper layers to the upper atmosphere. In others, a layer higher above is warmed again. Computers then calculate the spectrum that each type of atmosphere would produce. Those results are compared with the light James Webb actually collected. If a model produces an absorption feature that is too strong while the data show emission, that model does not fit. If another structure can reproduce the shape and intensity of the methane signal, it becomes a more plausible explanation. Through this process, models in which the atmosphere only cools with altitude could not explain the observation well. They caused methane to continue absorbing light, as it does on many other cold brown dwarfs. To create the excess light, the atmosphere required a region higher above that was significantly warmer. The entire process can be imagined as observing a house through closed windows. No one can step inside and place a thermometer in every room. But by studying the light escaping from the house and the way the glass alters its colors, it is still possible to infer which rooms are warm and where a source of heat may be operating. Of course, a model is not a direct photograph. It does not reveal a clearly visible band of hot gas suspended above the object. It only shows that, among the structures tested, an upper layer of warmer gas explains the data better than the alternatives. This distinction is important. What James Webb directly measured was light. The conclusion that the atmosphere contains a temperature inversion is inferred from the way that light was produced. Scientists therefore still need further observations to determine whether the current model is correct or whether another process remains missing. Even so, the methane signal cannot exist without a cause. Some part of the atmosphere is receiving energy. It may be confined to a thin layer, concentrated around the magnetic poles, or located within a hot region that moves in and out of view as the object rotates. At present, the data are not sufficient to determine its exact location. If the emitting region lies near the two poles, auroral activity becomes an appealing explanation. If it extends across the entire atmosphere, upward flows of internal energy may be more important, and if the signal changes over time, a large storm or moving hotspot could be contributing to the phenomenon. The first step is to consider how energy from the interior might travel upward. The object remains extremely hot in its deeper layers. Differences in temperature keep the material in motion, with warmer gases rising while cooler matter sinks, potentially creating vast circulation patterns. These motions do not necessarily remain confined to the deep atmosphere. They may generate waves that travel upward, much as winds and storms on Earth create disturbances throughout the atmosphere. As these waves enter regions of lower density, they can grow stronger and eventually break, releasing their energy as heat. If this mechanism is powerful enough, some of the internal heat could be carried into the upper layers. The problem is that scientists do not yet know whether the amount of transported energy would be sufficient to produce methane emission. They would need to understand the wind speeds, the strength of the waves, and the way heat is distributed around the entire object. Another possibility involves storms on an enormous scale. Brown dwarfs may rotate rapidly and contain powerful moving cloud bands, resembling the weather of giant planets but potentially far more violent. Such systems could create hot and cold regions and cause the object's brightness to change as it turns. If a storm carries warm gas upward from the deep interior, methane in that region may produce a different signal from the rest of the atmosphere. When the hot area rotates into view, the emission may strengthen. When it moves to the far side, the signal may fade. These variations have not yet been monitored long enough to support a firm conclusion. But if the methane emission changes in a regular cycle, it could help reveal the rotation rate and location of the glowing region. This would be one of the most important ways to distinguish atmospheric weather from auroral activity. Yet internal energy alone may still be unable to explain everything. On many giant planets, the upper atmosphere is so much warmer than expected that models based on convection and atmospheric waves continue to face difficulties. This suggests that additional processes involving magnetic fields and charged particles may be required. A powerful magnetic field could surround the object like an invisible cage. Charged particles entering this region could become trapped, accelerated, or guided toward particular areas. As they plunge into the atmosphere, their energy would be transferred to gas molecules through a series of collisions. Methane may be one of the molecules receiving that energy. After a collision, it can release infrared light before returning to its normal state. If billions of molecules undergo the same process, James Webb may be able to detect the excess emission from an immense distance. This mechanism resembles an aurora, though it would not necessarily produce the green or red curtains of light seen on Earth. Different atmospheric compositions generate different forms of radiation. Most of the signal may lie in the infrared, remaining completely invisible to human eyes. An infrared aurora could still carry an enormous amount of energy. It would not need to appear brilliant and visible light to heat the upper atmosphere. As long as enough charged particles were falling inward, temperatures near the magnetic poles could rise significantly. The greatest problem is determining where those particles come from. Earth receives them from the solar wind. Jupiter receives particles from the solar wind as well, but also gains additional material from Io. The brown dwarf being studied, however, has no nearby host star continuously releasing particles into its surroundings. Interstellar space still contains a small amount of plasma, though its density is extremely low. As the object moves through this environment, its magnetic field may capture some particles. It remains uncertain, however, whether this source could sustain the hot atmospheric layer and the strong methane signal that have been observed. An unseen companion or moon offers another possible explanation. If such an object releases gas, dust, or electrically charged material, the magnetic field could draw those particles into the system. Their long-term interaction might create a localized source of energy without requiring a stellar wind. Later observations suggested that this seemingly solitary world has another cold object nearby. The discovery does not prove that the two components are generating auroras for one another, but it makes magnetic interaction more worthy of consideration. A binary system may be far more complex than a single object drifting alone. Whatever the source of the energy may be, the final result is the same. An upper atmospheric layer is receiving more energy than expected. The glowing methane is simply the clearest trace James Webb has detected within that larger process. Other molecules may also be reacting, though their signals could be weaker or hidden beneath overlapping features. Certain gases may absorb energy and then transfer it to their surroundings. A chain of such reactions could alter the temperature structure without leaving behind one simple, unmistakable signature. This makes the atmosphere especially difficult to interpret. Scientists must understand not only its chemical composition, but also its winds, clouds, rotation rate, magnetic field, and sources of charged particles. Each factor can alter the way heat moves from one layer to another. The current models are only the first steps. They show that a warm upper layer is needed to explain the spectrum, but they cannot yet determine whether that layer covers the entire object or exists only within a small region. If it is confined to the poles, the average temperature of the whole atmosphere may not be especially high. Yet, an auroral region hot enough could still produce a clear signal when the light from the entire object is combined. In this way, a relatively small area could have a significant effect on the spectrum observed from far away. If the warm layer is widespread, the energy source may involve atmospheric waves or global circulation. In that case, methane emission would not be merely a sign of auroras, but also a record of how heat is transported through a world without a host star. It is also possible that both mechanisms are operating together. Internal energy may already be warming the atmosphere, while charged particles add further heat near the poles. In nature, the simplest explanation is not always the correct one, because several processes can work together to produce the same result. Distinguishing among these possibilities will require monitoring the light over longer periods. If the signal changes rapidly with rotation, the hot region may be concentrated in one location. If it remains stable across many cycles, the warm layer may extend over a much broader area. Observations at other wavelengths will also be essential. Some molecules respond strongly to heat, while others are more sensitive to charged particles. By combining many different signatures, scientists may be able to determine where the energy originates and how it affects the atmosphere. For now, the clearest conclusion is that an ordinary temperature structure cannot explain the data. A world that is gradually cooling from within possesses an upper atmospheric layer that is warmer than expected. This suggests that energy is not simply escaping outward and fading into space. Somewhere in the atmosphere, energy is being gathered, transported, or released. It does not appear in images as a flame, form an obvious source of light, or reveal where it begins. But methane has preserved the trace of that process within the infrared spectrum. A high atmospheric layer is warmer than expected. Methane is glowing, yet the energy source appears in no image. It can be recognized only through extremely subtle changes in the spectrum of a faint object nearly 47 light-years from Earth. If the energy does not come from starlight, the answer may lie in electricity, magnetic fields, and charged particles falling into the atmosphere like an invisible rain. Auroras are more than gentle ribbons of light drifting across the night sky. Behind their beauty lies an immense flow of energy connecting space with an atmosphere. Particles too small for human eyes to see plunge downward at tremendous speeds, colliding with the air and forcing atoms and molecules to release light. On Earth, the story begins with the Sunday. Our star sends not only light and heat toward the planet, but also a continuous stream of electrically charged particles into space. This flow of matter is known as the solar wind, and it can take several days to cross the distance between the Sun and Earth. As the particles approach our planet, they encounter the magnetic field surrounding Earth. This invisible shield deflects most of the solar wind, preventing the atmosphere from being directly exposed to the entire stream of high-energy particles. Some of the material, however, is still guided along magnetic field lines toward the two polar regions. There, charged particles plunge into the upper atmosphere and collide with oxygen, nitrogen, and many other molecules. After each collision, the atoms briefly receive additional energy. When they return to their normal state, they release that energy in the form of light. The colors of an aurora depend on the type of gas, the altitude, and the amount of energy being transferred. Oxygen can produce green or red light, while nitrogen contributes shades of blue and violet. Every auroral curtain is therefore the result of countless collisions taking place throughout the atmosphere. But the light is only the most visible part of the process. Most of the particle's energy does not become brilliant color. Instead, it is converted into heat, electrical currents, and chemical changes. Auroras can therefore warm the upper atmosphere, influence the movement of gases, and drive reactions that would not occur under ordinary conditions. On Earth, the source of the particles is fairly clear. The sun continuously supplies matter, while the magnetic field guides it. When a powerful solar storm is directed toward the planet, auroras may brighten, spread far beyond the polar regions, and sometimes appear in places where they are rarely seen. Earth, however, offers only a relatively mild example of auroral activity within the solar system. On Jupiter, the glowing rings around the poles are larger, more powerful, and almost continuously present. They do not depend entirely on what the sun sends toward the planet. Jupiter rotates extremely quickly, completing one turn in less than 10 hours. This motion carries its enormous magnetic field along with a vast population of charged particles trapped around the planet. The entire system behaves like an electrical machine spinning at tremendous speed. Jupiter's magnetic field is many times stronger than Earth's and extends far into space. It can capture particles, accelerate them, and guide them toward the atmosphere. When these streams plunge into the regions near the poles, they create auroras of extraordinary energy. But the solar wind is not the only source of material. A significant amount comes from Io, the innermost of Jupiter's 4 large moons. Io is the most volcanically active world known in the solar system. Its surface is constantly stretched by the gravitational pull of Jupiter and the neighboring moons. This continual flexing heats the interior and sustains hundreds of active volcanoes. Many plumes can rise hundreds of kilometers before their material escapes into space. Gas and dust from Io are quickly transformed into charged particles by sunlight and the surrounding environment. Jupiter's magnetic field then captures them and carries them around the planet. Over time, an immense ring of plasma forms along the moon's orbit. Io therefore acts like a small factory, continuously feeding material into Jupiter's magnetic machinery. These particles help create powerful electrical currents linking the moon with the planet's atmosphere. Near Jupiter's poles, that flow of energy leaves a distinct, bright mark within the auroral system. This shows that a celestial object does not need to rely entirely on stellar wind to sustain auroras. With a sufficiently strong magnetic field and a nearby source of material, it can maintain an active system of charged particles over long periods. This is an especially important detail when studying worlds without a sunday. Saturn provides a similar example. The planet has a magnetic field and auroras around both poles, but its surrounding environment also receives material from Enceladus. Although it is only a small moon, Enceladus continuously sprays water, ice, and gas from fractures near its south pole. Some of that material falls back to the surface, while the rest helps form Saturn's broad E-ring. Many particles are eventually ionized and absorbed into the planet's magnetic environment. In this way, a tiny moon can influence a region of space far larger than itself. Io and Enceladus show that auroral systems are not simply connections between planets and their host stars. Moons, magnetic fields, electrical currents, and escaping material can combine into a complex network. Even a small change on a moon can leave a trace within the atmosphere of a planet. These examples open an intriguing possibility for the cold brown dwarf observed by James Webb. Although it does not orbit a sun-like star, the object could still generate auroras if it possesses a magnetic field and a suitable source of charged particles. A celestial body does not need to be a star in order to have a magnetic field. Earth, Jupiter, Saturn, and many other planets generate magnetism through the movement of electrically conductive material in their interiors. A rapidly rotating brown dwarf with high temperatures and immense internal pressure may be able to sustain a similar mechanism. Deep inside it, matter is strongly compressed and exists in states very different from ordinary gas. As layers of electrically conductive material move, they may generate a magnetic field around the object. The field itself does not glow, but its effects may be detected through radio waves or auroral activity. In fact, some brown dwarfs have been observed producing powerful, repeating radio pulses. These signals often rise and fall with rotation, suggesting that the source may be connected to a fixed magnetic region. Each time that region turns toward Earth, telescopes receive another pulse. Such signals have shown scientists that brown dwarfs are not silent, dark masses of gas. They can possess powerful magnetic fields, immense electrical currents, and active auroral regions. Although they do not shine like stars, the space around them may still be filled with energy. What makes W1935 unusual is that it is much colder than most brown dwarfs previously found with signs of auroral activity. Rather than detecting the phenomenon first through radio waves, James Webb discovered a possible trace within the methane in its atmosphere. Methane does not create energy by itself. It simply responds to what is happening around it. If charged particles plunge into the upper atmosphere, they may collide with hydrogen, methane, and many other molecules, raising the temperature and changing the way those substances emit light. Under these conditions, methane may release infrared radiation. Human eyes would see no colorful ribbons stretching across the sky, but James Webb's instruments could still detect the increase in energy. If an aurora exists there, it may be almost entirely invisible to us. The sky of that world could remain dark in visible light. Only infrared wavelengths might reveal heated regions around the poles. Those glowing areas could be faint, broad, or change as the object rotates, but from a distance they would all blend into a single tiny infrared point. James Webb has not photographed a clearly defined auroral ring. The telescope cannot resolve the individual poles of an object 47 light-years from Earth. What it measures is the combined light of the entire atmosphere, within which the methane emission appears stronger than expected. Auroras therefore remain a hypothesis rather than a confirmed image. Scientists are drawing inferences from what is already known about Jupiter, Saturn, and radio-emitting brown dwarfs. The similarities help them build a possible explanation, but they do not guarantee that every detail is the same. A brown dwarf's atmosphere has temperatures, pressures, and gravity, unlike those of the planets in the solar system. Energetic particles may penetrate more deeply before coming to rest. Methane may respond differently. While the aurora may release most of its energy at wavelengths that earlier telescopes were not sensitive enough to observe. If the particles travel deep into the atmosphere, they will collide with denser material. Most of their energy may become heat rather than visible light. This could explain why the most prominent signatures are methane emission and an unusually warm upper atmospheric layer. But this hypothesis immediately leads to a major problem. To create an aurora, a magnetic field needs a source of charged particles. On Earth, those particles come from the Sunday. Around Jupiter, Io supplies a vast additional source of material. So where does this world without a host star obtain its particles? Interstellar space is not entirely empty. It contains extremely thin gas, dust, and a small amount of plasma. As a celestial object moves through this environment, its magnetic field may interact with the surrounding particles and guide some of them into the atmosphere. However, interstellar matter is spread very thinly. A handful of particles within a vast volume may not be enough to sustain powerful auroras and continuously heat the atmosphere. Scientists still do not know whether movement through space could provide the amount of energy required. Another possibility is that the magnetic field accelerates particles already present within the system. A rapidly rotating brown dwarf could pull plasma along with it, generating electrical currents and releasing energy. This mechanism would resemble what happens around Jupiter, where the planet's rotation plays a major role. Even then, however, the plasma must originate somewhere. Without a strong stellar wind, a nearby source of material would be needed to replace the particles that are gradually lost. This is where the idea of an unseen moon becomes especially intriguing. Such a moon would not need to be large. Io is only slightly smaller than Earth's moon, yet it has a powerful influence on Jupiter's entire magnetosphere. If a world with volcanoes, erupting plumes, or a surface that is constantly losing material orbited the brown dwarf, it could supply enough gas and dust to sustain the particle streams. At a distance of nearly half a century of light travel, a moon like this would be extraordinarily difficult to detect directly. It might be too small, too dark, and appear too close to the primary object in the sky. James Webb could collect the combined light of the entire system without separating a smaller moon from the shared point of light. Even if the moon could not be seen, its influence might still reveal itself indirectly. Auroral signals could vary with its orbital cycle. Radio emission might intensify whenever the moon passed through a particular region. Certain molecules in the atmosphere might also respond more strongly when the flow of particles increased. A broader possibility is that the material comes from a larger companion object. New observations suggest that the point of light once considered solitary may actually consist of two cold components lying close together. This makes the surrounding environment far more complex than scientists initially believed. Each object could possess a magnetic field of its own. As they move around one another, their magnetic regions might interact, stretch, and release energy. Particles occupying the space between the two components could also be accelerated and then guided down into one of their atmospheres. There is currently no evidence that this process is truly occurring. The two components may be too widely separated, or their magnetic fields may not be aligned in the necessary way. Even so, the discovery of a binary system means the object can no longer be regarded as a completely isolated world. Beyond particles supplied by a moon or companion, the energy may still come from the atmosphere itself. Powerful gas currents and waves rising from the deeper layers could heat the upper regions. In that case, methane emission would not be an aurora, but a trace of heat being transported through the atmosphere. The two mechanisms could even be operating together. Internal heat might create an atmosphere that is already relatively warm, while charged particles add further energy near the poles. From such a great distance, James Webb sees only the combined light and cannot yet separate the contribution of each process. To test the auroral hypothesis, scientists must search for independent evidence. Radio waves are one possible sign. If the object produces repeating radio pulses synchronized with its rotation, this would provide strong evidence that it possesses a magnetic field and streams of high-energy particles. Changes in the methane signal are also important. If the emission rises and falls on a cycle lasting several hours, the glowing region may be concentrated around a particular location. As the object rotates, the hot area would repeatedly move into view and then disappear from the side facing Earth. If the methane cycle matches the radio cycle, the connection with auroras would become far more convincing. Two different signals changing together with the object's rotation could indicate that both originate from the same magnetic region. Conversely, if the methane emission remains steady and shows almost no variation, the warm atmospheric layer may extend across the entire object. In that case, atmospheric waves or global heat circulation could play a greater role than localized auroral activity. Other molecules may also leave traces behind. Energetic particles would affect not only methane, but also hydrogen, ammonia, and many other compounds. Some reactions could produce new substances, helping scientists determine the altitude at which the energy is being released. Yet not every familiar signature seen on Jupiter would necessarily appear here. A denser atmosphere, stronger gravity, and different temperatures could cause ions to be destroyed before they have time to emit light. Auroras beyond the solar system may look very different from anything humans have observed before. This is why scientists must remain cautious. Methane emission is consistent with the possibility of auroras, but it cannot confirm the phenomenon on its own. Additional data from radio waves, changes over time, and other infrared wavelengths will be needed to assemble a complete picture. Whatever the final explanation may be, the discovery shows that worlds without a sun can remain intensely active. Darkness does not mean stillness. An object receiving no light from a host star may still possess winds, clouds, magnetic fields, and immense electrical currents. Within that darkness, auroras may not glow green or red. They may exist only as a warmer atmospheric layer, a brief radio pulse, or a band of methane emitting in the infrared. These faint traces are how a distant world reveals the energy machinery operating within and around it. On Earth, charged particles come from the Sunday. Around Jupiter, Io continuously replenishes the supply of material. At Saturn, Enceladus helps sustain the magnetic environment. But on the cold world now being observed, the source of the particles remains unknown. If auroras are truly occurring there, the energy entering the atmosphere must come from somewhere that has not yet been seen. It may begin deep within the object, in interstellar space, on a hidden moon, or within the nearby companion. This is the next stage of the investigation, tracing 3 possible sources of energy concealed within the darkness. A mysterious signal cannot be explained simply by choosing the most appealing answer. Auroras may seem like a good fit, but a hypothesis has value only when it produces evidence that can be tested. Scientists must therefore examine each possible energy source in turn, determine the conditions it would require, and identify the weaknesses in every explanation. The first possibility lies within the object itself. Although a brown dwarf cannot sustain nuclear reactions like a true star, it still retains an enormous amount of heat from its formation. That energy continues to escape outward, keeping the atmosphere in motion for millions or even billions of years. This world can be imagined as an immense sphere of gas still glowing with heat deep inside. Its lower layers are subjected to tremendous pressure and are far hotter than the atmosphere above. The temperature difference sets the material in motion, creating rising currents of warm gas and cooler currents that sink in their place. This process is known as convection, but it is not entirely unfamiliar. In a pot of water being heated, warmer water rises from the bottom while cooler water sinks to replace it. Inside a brown dwarf, a similar motion may occur on a vastly greater scale. These gas currents do more than transport heat. They can also generate powerful winds, broad cloud bands, and weather systems that endure for long periods. One region of the atmosphere may be warmer, brighter, or contain a different type of cloud from the area beside it. If the object rotates rapidly, these currents may be drawn into bands encircling the entire atmosphere. Jupiter offers a clear example, with its alternating bright and dark cloud bands and storms that can persist for centuries. On a brown dwarf, similar systems may be even more powerful because of the stronger gravity and greater abundance of internal heat. Deep currents and storms may generate waves that travel into the upper atmosphere. These are not waves of water, but regions of gas that compress and expand as energy moves through the atmosphere. As they travel, the waves carry some of the heat and motion from the place where they formed. When they reach thinner layers of gas, the waves may grow in amplitude and eventually break apart. Their energy of motion is then released as heat, warming the surrounding region. This is one mechanism that could help explain why the upper atmosphere is hotter than expected. On Earth, atmospheric waves also carry energy from lower layers to higher ones. Although the environment is very different, the basic principle remains the same. A process occurring deep below can leave an effect hundreds or thousands of kilometers away from its original source. This makes internal heat a reasonable explanation. The object does not need to receive light from an outside star because it already contains a vast reservoir of energy within itself. The remaining question is whether enough of that energy can be carried into the upper atmosphere. The glowing methane shows that one atmospheric layer is receiving a significant amount of energy. If ordinary gas currents were the only cause, the heat might spread too widely to produce such a distinct signal. To explain the observation, the waves or storms would need to concentrate enough energy within the precise layer containing methane. Scientists must also determine whether the warm region covers a large area or is confined to one location. If the atmosphere is being heated globally, internal energy becomes a stronger explanation. If the signal appears only within a small region, perhaps near a magnetic pole, another mechanism may be more important. Changes over time could help distinguish between these possibilities. A localized hot region would rotate into and out of view from Earth, causing the light to rise and fall periodically. A warm layer covering a broad area, by contrast, might produce a more stable signal. For now, the observations do not extend long enough to reconstruct a complete weather map. James Webb has provided only a highly detailed slice of the spectrum. From it, Scientists can infer that an upper atmospheric layer may be warming, but they cannot yet determine where that heat originates. Internal energy is therefore a possibility worth considering, but it cannot yet be confirmed. It explains how a world without a sun can remain active. Even so, it is still unclear whether winds, storms, and atmospheric waves can make methane glow as strongly as the observed signal suggests. The second possibility comes from the interstellar environment. Space is often described as a perfect vacuum, but it still contains matter. Between star systems lie extremely thin gas, tiny grains of dust, and electrically charged particles moving through the darkness. The density of this material is extraordinarily low compared with Earth's atmosphere. A vast volume may contain only a few particles, yet, as a strongly magnetized object travels through this environment over long periods, it may still interact with the surrounding matter. A magnetic field can be imagined as an invisible region of influence surrounding the object. When charged particles enter it, their paths begin to curve. Some may be pushed away, while others become trapped or guided down toward the atmosphere. If the brown dwarf moves rapidly enough through the interstellar medium, the front of its magnetic field may be compressed like the bow of a ship moving through water. Particle streams and electrical currents could form along this boundary, allowing some of the energy of motion to be transferred into the atmosphere. This mechanism would not require stellar wind from a host star. The object's own motion through space could create the interaction. It would be similar to an electrical conductor moving through an environment filled with charged particles, continuously disturbing the material in its path. The weakness of this hypothesis is the extreme thinness of interstellar matter. Even if the magnetic field captures some particles, the total amount of energy collected may not be enough to heat the atmosphere and produce strong methane emission. To test this possibility, scientists would need to know the object's velocity, the strength of its magnetic field, and the density of matter in the region through which it is traveling. Only by combining all three factors could they estimate how much energy is actually entering the atmosphere. If the surrounding environment is denser than average, the supply of particles could be greater. A thin cloud of gas or an unusual region of plasma might temporarily increase the interaction. So far, however, there is no clear evidence that the object is passing through such an area. If the interstellar environment is the main source, the activity may change slowly as the object travels through regions of differing density. In that case, the methane signal would not necessarily repeat with a rotation period of several hours, but might instead vary over much longer spans of time. Radio waves could also provide a clue. If particles are being accelerated within the magnetic field, they may produce a distinctive radio signal. Detecting repeating pulses would show that a magnetic engine is operating, even if the original source of the particles remained unknown. The second possibility has therefore not been ruled out. Interstellar space may supply some of the matter and energy, but because the environment is so thin, many researchers suspect that a stronger local source would be needed to sustain the phenomenon over long periods. This is where the third possibility becomes especially intriguing. A small moon or another nearby object might continuously release material into space. The magnetic field could then capture that matter and turn it into a source of particles for auroral activity. A clear example of this mechanism already exists in the solar system. Io is small compared with Jupiter, yet its volcanic activity constantly pumps gas and dust into the planet's magnetosphere. The material becomes electrically charged, is carried around Jupiter, and eventually participates in extremely powerful electrical currents. If W1935 has a similarly active moon, that moon would not need to shine brightly. Volcanoes, erupting plumes, or a surface that continuously loses material could be enough to supply plasma throughout the system. A small world could create an influence far greater than its size would suggest. Such a moon would be extraordinarily difficult to detect from a distance of 47 light-years. It might be only a few thousand kilometers wide, much darker than the brown dwarf, and appear almost directly beside the primary object from Earth. The light from both would blend into the same tiny point. Even James Webb would struggle to separate an object so small and so close to the main source of light. Scientists might therefore have to detect it through indirect effects, a repeating cycle in the auroral signal, a subtle motion of the brown dwarf, or an unusual variation in brightness could reveal the moon's presence. If the moon followed a stable orbit, the particle flow might increase whenever it passed through a particular region of the magnetic field. Methane emission or radio waves could then repeat according to the orbital period. This pattern would be very different from variations caused by the brown dwarf's own rotation. No such signal has yet been confirmed. The moon hypothesis still rests on comparisons with Jupiter and Saturn. It demonstrates that the mechanism is possible, but does not prove that a small object is actually hidden within the system. New observations have broadened this possibility even further. The point of light once believed to be a solitary object appears to have another cold component nearby. The system is therefore not completely isolated, even though neither component is a luminous star. The companion is much larger than an ordinary moon. It may also possess an atmosphere, a magnetic field, and moons of its own. Its presence makes the surrounding environment far more complicated, because there are now at least two sources of gravity and potentially two magnetic regions. If the two magnetic fields are strong enough and aligned in the right way, they may interact. As magnetic field lines are stretched, twisted, and rearranged, energy can be released. Similar processes occur during magnetic eruptions on the Sun and within the magnetospheres of certain planets. Particles between the two objects could be accelerated during this interaction. They might then plunge into one of the atmospheres, heating its upper layers and exciting methane. It is an intriguing possibility, but the available data are not yet detailed enough to confirm it. The distance between the two components is also an important factor. If they are too far apart, their magnetic fields may not reach one another, or any interaction between them may be too weak. But if the fields extend far enough, they could still create a bridge of energy even across hundreds of millions of kilometers. Their orbital motion could cause the strength of that interaction to change over time. When the two components draw closer together, or their magnetic fields become favorably aligned, the emission may intensify. As they move into different positions, the flow of energy could weaken again. Testing this possibility, however, would require astronomers to monitor the system for many years. Its orbital period is expected to last for decades, meaning any changes would unfold very slowly. A few isolated observations cannot yet reveal a clear connection. Another unresolved problem remains. The earliest observations collected the light of the entire system as a single signal, so scientists do not yet know which component is producing the methane emission. It may come from the larger object, but the source could also lie within the smaller, colder companion. If the signal originates from the companion, the original interpretation would need to be reconsidered. The temperature, gravity, and magnetic field of the emitting object could differ from what researchers initially assumed. Separating the spectra of the two components is therefore an essential next step. The idea of a local source of material remains appealing because it addresses the greatest weakness of the auroral hypothesis. A powerful magnetic field may exist, but it still requires charged particles to operate. A moon or companion object could supply the material that the thin interstellar environment cannot provide in sufficient quantities. Appealing, however, does not mean proven. There is no image of a moon releasing material, no plasma stream has been observed directly, and no clear cycle has yet linked the signal to an orbit. The current evidence allows scientists to say only that this possibility has not been ruled out. The three potential energy sources therefore remain side by side. Internal heat and atmospheric waves may be warming the upper atmosphere. The interstellar environment may provide a small number of particles. A moon or companion object may create a stronger local source of plasma. There is also no natural reason to assume that only one mechanism must be involved. Real worlds are often more complicated than simple models. Some of the heat may rise from within, while auroral activity adds further energy around the polar regions. The interstellar environment could supply the initial particles, while a small moon maintains a larger flow of material. These processes may operate together, change over time, and combine to produce the spectrum observed by James Webb. To distinguish among them, scientists need specific signatures. Energy rising from within may heat a broad region and create variations connected to weather. Auroras may be concentrated around the poles, change with rotation, and appear alongside radio emission. A moon could create a cycle tied to its orbit. Interactions between the two larger components might vary over many years. Each energy source would leave behind a different rhythm in time, and sufficiently long observations may allow scientists to separate them. The chemical composition may also provide clues. High-energy particles can create ions and reaction products that differ from those produced by ordinary heating. Detecting those traces would strengthen the auroral explanation. In Jupiter's atmosphere, certain ions emit infrared light and help scientists track auroral activity. Researchers have therefore searched for similar signatures in the spectrum of the cold brown dwarf. If the same mechanism is operating there, at least some familiar traces might be expected to appear. But the data do not reveal them as clearly as predicted. The methane is glowing, and the upper atmosphere appears to be warming. Yet some of the indicators commonly associated with Jupiter's auroras are weak or absent. This makes the explanation more complicated. That absence may have two meanings. Either auroras are not the main source of energy, or auroral activity on a brown dwarf occurs under conditions entirely unlike those on Jupiter. The particles may penetrate deeper into the atmosphere, where high pressure quickly destroys the familiar ions. Jupiter, therefore, cannot be treated as a perfect model. It provides only a starting point. Stronger gravity, a denser atmosphere, and different temperatures may cause the same process to leave behind an entirely different set of signatures. This is what keeps the investigation open. Auroras remain a plausible explanation, but they have not been confirmed. Internal heat may still play a major role, while an object not yet clearly observed could be supplying material. The most certain evidence remains the light itself. Methane is emitting more strongly than expected, showing that an atmospheric layer has received additional energy. That energy source has not appeared in any image, nor has it produced the full set of familiar signatures. If auroral activity is truly taking place, it may not resemble anything we see on Earth or Jupiter. It could occur deeper within the atmosphere, glow mainly in the infrared, and alter methane in a way that has never been observed before. The absence of familiar indicators does not necessarily disprove the auroral hypothesis. It may instead reveal that the phenomenon on this cold world operates according to different rules from those governing the giant planets of our solar system. To understand that difference, we must look deeper into the region where charged particles collide with the atmosphere and determine why some of the expected signatures disappear. Jupiter gives us a useful model to begin with. It has a powerful magnetic field, immense auroras, and a hydrogen-rich atmosphere that is relatively similar to what scientists imagine for a cold brown dwarf. But when every detail of Jupiter is applied to the world observed by James Webb, gaps quickly begin to appear in the picture. On Jupiter, charged particles are guided by the magnetic field toward the polar regions. As they plunge into the atmosphere, they collide with hydrogen and create distinctive charged molecules. These molecules can emit infrared light, helping scientists identify where auroral activity is occurring and which layers of the atmosphere are being heated. They can be thought of as warning lights within the atmosphere. When the flow of particles becomes strong enough, their infrared signals grow more visible. By observing these traces, scientists can monitor auroral activity, even though the entire process cannot be seen directly with the naked eye. Saturn leaves behind similar signals. Its auroras vary with the solar wind, the planet's rotation, and the amount of material trapped within its magnetic field. Charged molecules have therefore become an important part of reconstructing how energy travels from the atmosphere. So when glowing methane was detected on the cold brown dwarf, researchers searched for these familiar signatures. If auroras were heating the upper atmosphere, the charged molecules commonly observed on Jupiter might also be present in the data. But James Webb did not detect a signal clear enough to confirm them. Methane is emitting infrared light, and the temperature structure suggests that the upper atmosphere is being heated. Yet, the familiar signatures usually associated with Jupiter's auroras are far weaker than expected. This creates a problem. If the same mechanism is operating, why does the atmosphere not leave behind the same collection of traces? Is the auroral hypothesis wrong? Or is the phenomenon unfolding in an entirely different way? The answer may lie in the depth at which the energetic particles come to a stop. On Jupiter, many particles are halted relatively high in the atmosphere. The gas there is still thin enough for charged molecules to survive and release light before being destroyed. On a brown dwarf with stronger gravity, those particles may continue much deeper. They pass through the thin upper atmosphere before losing most of their energy in regions where the gas has already become dense. The environment in which the collisions occur would then be entirely different from Jupiter's auroral regions. Within these denser layers, molecules are packed closely together and collide constantly. An ion that has just formed may be destroyed almost immediately. Its energy is transferred to surrounding molecules rather than escaping as infrared light that a telescope could detect. This can be imagined as releasing a drop of dye into 2 glasses of water. In one glass, where the water is nearly still, the color spreads slowly and remains clearly visible for a while. In the other, where the water is being stirred rapidly, the dye disperses at once and disappears before it can form a distinct trail. Ions in the atmosphere may experience something similar. They are still created by energetic particles, but they survive for too little time to produce a strong signal. Their energy does not vanish. Instead, it becomes heat, warming the surrounding gas. If this mechanism is correct, the absence of familiar signatures would not disprove the auroral hypothesis. It would simply mean that the auroras are occurring deeper in the atmosphere, where high pressure prevents charged molecules from surviving for long. Methane may become the more visible indicator because it responds to the heat produced in that region. This could also explain why methane glows while other ions remain nearly silent. Charged particles plunge downward and heat a dense atmospheric layer. Methane within that region absorbs the energy and emits infrared light, while the charged molecules are destroyed too quickly to produce signatures of their own. Even so, this remains only one possible explanation. James Webb cannot directly see where the particles come to rest. It collects the combined light from the entire object, and scientists then use models to infer what may be happening behind the data. To understand the process more clearly, researchers need to know how strong the gravity is. A more massive object holds its atmosphere more tightly, causing the density to increase rapidly with depth. Energetic particles may therefore encounter a much thicker wall of gas than they would on Jupiter. Temperature also creates a major difference. Although this world is described as a cold brown dwarf, it is still far hotter than the giant planets of the solar system. A warmer atmosphere changes the speed of chemical reactions and may shorten the lifetimes of certain molecules. The rotation rate may influence the entire system as well. Many brown dwarfs complete a full rotation in only a few hours. This rapid motion carries the atmosphere and magnetic field along with it, generating powerful electrical currents while also stretching energetic regions into broad bands. On Jupiter, auroras are clearly concentrated around the 2 poles. On an object rotating more rapidly or possessing a different magnetic structure, the regions where particles descend may become scattered, extended, or displaced. When viewed from far away, the signals from these separate areas would blend together. The magnetic field itself may not have a simple shape. Earth's field resembles a magnet with 2 main poles, but many celestial objects may possess far more complicated magnetic regions. Some field lines extend outward into space, while others close together near the object. If the magnetic field is strongly tilted relative to the rotation axis, the auroral regions will continually shift position as the object turns. The methane signal may rise and fall over time, but that pattern can be recognized only through observations that are both long and frequent enough. The available data are not yet sufficient to construct such a map. James Webb has detected the unusual signal, but it has not continuously monitored the object through many rotations. Scientists therefore do not know whether the glowing methane remains stable across the entire atmosphere or is concentrated within only a few regions. If the emission comes from the poles, its intensity may change in a regular pattern. As a hot region rotates toward Earth, the signal would strengthen. When it moves around to the far side, the amount of infrared light would decrease. If no clear variation appears, the warm layer may cover a large portion of the atmosphere. In that case, internal energy, atmospheric waves, or broad circulation patterns may play a more important role than localized auroral activity. This is why methane alone cannot support a final conclusion. The molecule reveals that energy is present, but it does not identify where that energy comes from. Auroras, weather, and heat transport can all change the way methane emits light. Scientists need to gather many pieces of evidence at once. The temperature structure reveals which atmospheric layer is warming. Changes over time can show whether the emitting region is localized. Radio waves may reveal the presence of a magnetic field and streams of high-energy particles. If a radio pulse appears regularly with each rotation, it would be strong evidence that the object possesses an active magnetic region. If the methane signal changes on the same cycle, the two signals may originate from the same auroral zone. On the other hand, if no radio waves are detected while the methane continues to glow steadily, internal energy would become a more compelling possibility. Even so, the absence of radio emission would not be enough to rule out a magnetic field, because the signal may simply be too weak or directed away from Earth. Auroral radio waves are often emitted in narrow beams. If the beam never sweeps across our position, telescopes will detect nothing, even while the phenomenon continues. Radio silence, therefore, does not always mean that auroras are absent. The atmospheric chemistry may provide additional clues. High-energy particles do more than heat methane. They can also break apart many other molecules. The fragments may then recombine to form new compounds. If these chemical products are detected, they may reveal that the atmosphere has been affected by charged particles. However, many of these traces are extremely weak and can easily overlap with signals from water, ammonia, or other carbon-bearing molecules. Clouds make the analysis even more difficult. A thick cloud layer can conceal light from deeper regions and make certain signatures appear weaker than they truly are. Cloud particles also scatter light, changing the shape of the spectrum in ways that can be misleading. Clouds on a brown dwarf may be very different from the familiar water clouds of Earth. Depending on the temperature, they may contain a variety of compounds and form at different altitudes. A cloud layer in the right location could hide auroral signatures while still allowing methane emission to escape. A single spectrum is therefore not enough to reconstruct the entire atmosphere. It is like trying to understand a city using only the light that passes through a bank of fog. A few brighter regions may remain visible, while many streets and power sources stay concealed. Jupiter helps scientists understand what to search for, but it cannot serve as a perfect duplicate. The planet receives energy from the Sun, gains plasma from its moon Io, and has an atmospheric structure that has been observed at close range by multiple spacecraft. The distant brown dwarf does not share exactly the same conditions. It does not orbit a bright star, has stronger gravity, is hotter, and may rotate more rapidly. Every one of these differences affects how energetic particles enter the atmosphere and how light is emitted. The same particle stream might produce a bright aurora on Jupiter, but create only a warm atmospheric layer here. The same type of ion may survive long enough to glow on the giant planet, yet be destroyed almost immediately in a denser, hotter environment. This reflects an important principle of science. Comparisons are extremely useful as a starting point, but they cannot replace direct observation. A newly discovered object may resemble familiar worlds in certain ways, while following very different rules deeper within its atmosphere. The phrase Jupiter-like aurora should therefore be understood only as an initial direction for interpretation. It does not mean that the sky there contains glowing rings identical to Jupiter's, nor does it mean that the same molecules must appear with the same intensity. Auroras on a brown dwarf could be dark, invisible light, powerful in the infrared, and occur at much higher pressures. They may produce none of the familiar colors while still delivering a significant amount of energy into the atmosphere. If so, glowing methane would not be a detail that falls outside the auroral model. It may be a signal better suited to this unfamiliar environment. The familiar ions disappear, while methane becomes the molecule that records the heat left behind by the particles. But before accepting that explanation, researchers must still determine where the particles come from. An aurora cannot exist through a magnetic field alone. It requires charged matter that can be accelerated, guided into the atmosphere, and driven into the collisions that release energy. For a time, the most intriguing possibility was an undiscovered moon. Such a moon might continuously release material into space, much as Io feeds Jupiter's magnetosphere. Although small and dark, it could still influence the entire atmosphere of the larger object. A world like this would be difficult to observe directly. At a distance of 47 light-years, it might appear so close to the main source that the two images blend together. Scientists could search for it only through subtle changes in motion or variations in the auroral signal. If the moon completed an orbit every few days, the emission might rise and fall according to that cycle. If it continuously released material, the space around the brown dwarf could contain a ring of plasma, similar to the environment surrounding Jupiter. So far, however, no clear cycle has confirmed this hypothesis. A small moon is not the only possibility. A larger object may also be present, but so cold and faint that the earliest observations could not separate it from the primary source. If so, the magnetic environment and supply of material within the system would be far more complex. Later, deeper observations with James Webb began to explore this very possibility. Rather than analyzing only the combined light, scientists tried to determine whether the tiny infrared point was truly a single object. The result changed the story. The point, once considered an isolated brown dwarf, turned out to contain two nearby components. Both are extremely cold and faint, yet separated clearly enough for James Webb to reveal that they are not a single object. This discovery did not immediately confirm auroras or explain the glowing methane. The companion is not a luminous star capable of heating the atmosphere from outside. Its existence, however, opened an entirely new system for scientists to consider. The two components may possess separate magnetic fields, moons, and plasma environments. They may interact directly or indirectly as they orbit one another. Material trapped between the two magnetic regions could provide the source of particles missing from the auroral hypothesis. More importantly, the first observations could not determine which component was producing the methane emission. The signal may come from the primary object, from its companion, or from both together. When their light is blended into a single point, every original model must be reconsidered carefully. If the emission truly originates from the smaller component, its temperature, mass, and atmospheric structure would differ from what scientists initially assumed. A colder object producing a stronger signal would raise even more questions about the source of its energy. If both objects are producing methane emission, the system may contain a more widespread mechanism rather than a phenomenon occurring on only one component. Determining this will require separating the spectrum of each object during future observations. The discovery of the binary system also makes the moon hypothesis more difficult to test. Each component may have its own smaller orbiting bodies. A moon could supply plasma to one object, while the other component merely alters the motion and magnetic structure of the system as a whole. The distance between the two objects is great enough that they cannot heat one another as a star heats a planet. Magnetic fields, however, may extend far beyond the visible dimensions of the objects themselves. If those fields are strong enough, their magnetic regions could still meet or influence the environment between them. As magnetic field lines are stretched and rearranged, energy may be released suddenly. Charged particles in the surrounding region could be accelerated and then driven into the atmosphere. This process might produce bursts of emission that vary with the object's orbital positions. For now, however, this remains speculation. No stream of material has been observed between the two components, no magnetic map has been created, and no clear orbital variation has been detected. The binary system has introduced a new possibility, not a final answer. What is certain is that the simple picture of a solitary world is no longer correct. The environment once thought to be almost empty now contains at least two cold objects. Each may carry its own atmosphere, magnetic field, and smaller systems that have yet to be observed. This change is important for interpreting the methane. The energy source may not come only from within one object or from interstellar space. It could also emerge from the relationship between the components within the same system. Even so, the principle of caution must remain. James Webb has observed the methane signal and resolved the two objects. Auroras, magnetic interactions, and moons supplying plasma are still explanations waiting to be tested. Auroras cannot be confirmed simply because methane is glowing, nor can they be ruled out merely because a few Jupiter-like signatures are missing. Different environments may cause the same process to leave behind very different traces. To move forward, scientists will need to combine several kinds of observations. They must separate the light from the two components, monitor the methane over time, search for radio waves, and determine whether the signal changes with rotation or orbital motion. If the methane and radio emission rise and fall together over a short cycle, an auroral region would become a strong explanation. If the variations unfold over many years and correspond to the motion of the binary system, interactions between the two components would deserve greater attention. If no clear variation appears, the warm atmospheric layer may be sustained by internal energy. In that case, auroras may play only a secondary role, or they may not be necessary to explain the full signal at all. The final picture may contain more than one source of energy. Atmospheric waves, magnetic fields, interstellar particles, and material from a companion object could all contribute. Nature is not required to choose a single, simple explanation. Jupiter provided the first model, but this cold world is showing that auroras may take more forms than humans have ever known. They may occur deep within the atmosphere, conceal the familiar ions, and leave only methane glowing in the infrared. For a time, the idea of an invisible moon seemed like the most reasonable way to explain the source of the particles. But as the faint point of light came into sharper focus, the investigation moved in a new direction. The world once believed to be alone turned out to contain more than one celestial object. In the earliest observations, W1935 appeared as nothing more than a tiny point of infrared light. At a distance of nearly 47 light-years, even an object many times more massive than Jupiter is reduced to a faint speck against the sky. But when James Webb looked more closely, that seemingly solitary point began to separate into two cold worlds lying near one another. The discovery immediately changed the way scientists imagined the entire system. The object once thought to be an isolated brown dwarf turned out to have a companion. Both are extremely cold by stellar standards, emit most of their energy in the infrared, and remain almost completely invisible to human eyes. The distance between the two components is greater than the distance between Earth and the Sun. If placed within our solar system, they would not sit close together like Earth and the Moon. Yet they are still near enough for gravity to hold them within the same system as they slowly orbit one another in the darkness. This means that the original point of light was not a single object. The light collected by earlier instruments may have been a blend from both components. Before they could be separated, every estimate of temperature, atmospheric composition, and methane may have contained traces from both worlds. The companion is not a bright star like the Sun. It does not produce enough light to heat the atmosphere of the other object in the usual way. The discovery of the binary system therefore did not immediately solve the question of why methane is emitting infrared light. Had a luminous star been found nearby, the explanation might have been relatively simple. Starlight could heat the upper atmosphere and create a temperature increase with altitude, but both components in this system are far too cold and faint to play the role of a Sun. The mystery did not disappear. It simply took on a more complicated form. Instead of asking where a solitary world obtains its energy, scientists must now ask whether two cold objects are influencing one another in a way that has not yet been observed. The first possibility involves magnetic fields. Each brown dwarf may possess a magnetic region surrounding it. If both generate sufficiently strong fields, the space between them may not be quiet at all, but filled with magnetic field lines, electrical currents, and moving charged particles. A magnetic field cannot be seen directly. It reveals its presence only through its effects on the surrounding matter. When a charged particle enters a magnetic region, its path may bend, accelerate, or be guided toward one of the two atmospheres. If the magnetic regions extend far enough, they may influence the same area of space. Their field lines could be stretched, twisted, or rearranged as the two objects orbit one another. Under certain conditions, this process may release energy and drive particles down into the atmosphere. A similar phenomenon occurs on the Sun when magnetic regions change suddenly and release powerful eruptions. On a smaller scale, Earth's magnetic field is continually stretched and rearranged by the solar wind, carrying energy toward the polar regions. There is no powerful stellar wind in this cold binary system like the one surrounding Earth. However, the orbital motion and rapid rotation of the two components may generate electrical currents of their own. If plasma exists in the space between the worlds, their magnetic fields would have material to capture and accelerate. That plasma could begin as gas escaping from an atmosphere or material released by smaller, undiscovered moons. With a continuous supply of matter, the entire system could operate like an enormous electrical machine. The particles could then plunge into the upper atmosphere and cause methane to glow. For now, however, this remains only a possibility. The distance between the two components is considerable, so their magnetic fields would need to extend very far to interact directly. Scientists do not yet know how powerful the magnetic region around either object may be or whether the two fields actually reach one another. Another possibility is that the two components do not need to connect directly. Their orbital motion could alter the particle environment throughout the system, allowing one object to capture material released by the other. Those particles might take a long time to travel across the system, yet still provide an additional source of energy. If one component produces an atmospheric wind, escaping material could spread through the surrounding space. As the other object passes through that material, its magnetic field could interact with it. This would not resemble a star heating a planet, but rather two magnetic machines sharing the same environment. The discovery of the binary system also broadens the moon hypothesis. Previously, scientists might have searched for a single moon around one object. Now, each component could possess its own satellites, increasing the number of potential sources of material. A small moon would not need to shine brightly. It would only need to be geologically active or continuously lose material. Plumes of gas, dust, or ice could escape into space, become trapped by a magnetic field, turn into plasma, and create particle streams directed toward the atmosphere. Within the solar system, Io shows that a small moon can influence an entire giant planet. Enceladus also demonstrates that plumes from a tiny world can inject material into the vast environment surrounding Saturn. An unseen moon therefore remains a physically plausible explanation. At a distance of nearly 47 light-years, detecting such an object would be extraordinarily difficult. Even the two large brown dwarfs were once blended into a single point of light. A much smaller moon would almost completely disappear within the infrared glow of the object it orbits. Scientists may have to detect a moon through its influence rather than through a direct image. It might cause the primary object to wobble slightly, produce small eclipses, or make an auroral signal vary with its orbital period. Recognizing these effects, however, would require many precise observations. The most important question, following the discovery of the binary system, is where the methane signal actually originates. The initial data collected light from both components at once. The unusual emission feature could therefore belong to the larger object, the companion, or a combination of both. If the emission comes from the primary component, the earlier models may still be broadly correct. Its atmosphere would need to contain a warm upper layer powered by auroras, atmospheric waves, or another mechanism. The companion would then simply introduce an additional possible source of particles. But if the glowing methane comes from the smaller, colder component, the entire picture would change. The temperature, mass, and gravity used in the original models may not belong to the true source of the signal. A colder world producing a warm atmospheric layer would raise an even more difficult question. It is also possible that both components contribute to the signal. One object may produce ordinary methane absorption, while the other creates strong emission. When their light is blended together, the final spectrum could take on a complex shape that no single object model can easily explain. It would be like hearing two voices at once through a single microphone. Unless each speaker can be separated, it is difficult to know which sound belongs to whom. James Webb has revealed that there are two sources, but more precise observations will be needed to hear each voice individually. Separating the light is not simple. In the sky, the distance between the 2 points remains extremely small. The telescope must observe at the right wavelengths, where the brightness difference between the components is large enough, or the image is sharp enough to prevent their light from overlapping. Each component may also appear brighter in one part of the infrared spectrum and fainter in another. One wavelength may reveal the primary object more clearly, while another makes the companion stand out. Scientists must therefore choose their observing methods with great care. Once the spectra can be separated, scientists will be able to determine where the methane emission originates. If only one component carries the signal, the source will become clear. The temperature and atmospheric composition of that specific object can then be used to build more accurate models. The discovery of the binary system will also help estimate the masses of both components. By tracking their motion around one another, scientists can determine the strength of their mutual gravity. From the orbit, they will be able to infer how much each object weighs without ever touching them directly. Mass is important because it determines gravity, pressure, and the way an atmosphere retains particles. A more massive object will have stronger gravity, allowing energetic particles to travel deeper into the atmosphere before coming to a stop. This directly affects the signatures left by auroral activity. Mass also helps scientists estimate age and cooling rate. Brown dwarfs do not shine steadily like stars, but gradually cool over time. Two objects with the same temperature but different masses may be at entirely different stages of evolution. If the system is young, both components may still retain a great deal of heat from their formation. Their internal energy would then be stronger and might be transported into the upper atmosphere. If the system is old, the remaining internal heat would be weaker, making auroras or magnetic interactions more important possibilities. Tracking the orbit will take time. The two components do not complete a revolution around one another in only a few days or months. Their orbit may take decades, so astronomers have observed only a very small portion of their path. Each time James Webb or another telescope observes the system, the relative positions of the two objects may shift slightly. Over many years, those measurements will gradually form a path of motion. Only then will their masses and the shape of their orbit begin to emerge. During that time, the methane signal must also be monitored. If it changes rapidly over several hours, the cause may be connected to the rotation of one component. If it changes slowly over many years, orbital motion or interaction between the two objects will deserve greater attention. The rhythm of change is one of the most important clues. An auroral region rotating with an object would repeat on a short cycle. A moon could produce a longer cycle. Interactions between the two larger components might vary over years or decades. If the methane emission grows stronger when the two objects reach a particular position in their orbit, the magnetic environment between them may be changing. If the signal does not depend on their orbit, the energy source may lie mainly within the atmosphere of one component. Radio waves must also be compared with this motion. A powerful magnetic field can often produce radio pulses, especially when particles are accelerated around the polar regions. If those pulses appear at the same time the methane emission intensifies, the auroral hypothesis would become stronger. But if only the methane changes, while the radio sky remains completely silent, no firm conclusion can yet be drawn. The radio beam may not be directed toward Earth, or the signal may simply be too weak to detect. Many kinds of data must therefore be combined before one explanation can be chosen. The discovery of the binary system also raises questions about how the two objects formed. They may have been created together when a cloud of gas divided, much like a pair of stars that never gained enough mass to become true stars. After forming, they continued orbiting one another and slowly cooling. If they were born at the same time, both may have roughly similar ages and initial compositions. This would make the system a natural laboratory. The two worlds share a common origin, yet may differ in mass, temperature, and atmospheric activity. The differences between them could help scientists understand why one component produces methane emission, while the other does not. If only one is highly active, the cause may lie in its magnetic field, rotation rate, or the presence of a moon, rather than in its age or formation environment. If both display similar signatures, the energy source may be more common among extremely cold brown dwarfs. Methane emission would then no longer be a rare phenomenon belonging to a single object, but perhaps a feature of a group of worlds that has not yet been studied closely enough. At present, only a small number of cold brown dwarfs have been examined in detail. They are too faint for older telescopes to collect high-quality spectra. James Webb is only beginning to make it possible to study objects that once nearly vanished into the darkness. The discovery of two components, therefore, changes more than the story of this particular system. It suggests that some points of light once considered solitary objects may actually be unresolved binaries, This could affect earlier estimates of their temperatures and masses. When the light of two objects blends together, the system appears brighter than a single object. Without knowing that two sources are present, scientists might conclude that one object is larger or hotter than it truly is. Resolving the binary helps correct that picture and makes the models more accurate. The same applies to methane. A combined spectrum may create a signal that no single atmosphere can easily reproduce. Once the two spectra are separated, part of the mystery may become simpler, though new differences may also emerge. The discovery therefore opens a possible path toward an answer while creating additional questions. It provides a potential source of material and interaction for auroral activity, but also makes the true location of the methane signal uncertain. Each new answer divides the mystery into more directions for investigation. What is certain is that this cold world is not completely alone. Beside it lies another object, equally faint and cold, and unable to shine like a star. Together, they move through a system without a sun, held to one another by gravity in the darkness. Neither component is bright enough to explain the warm atmospheric layer directly, but the existence of two worlds creates possibilities that a solitary object would not have. Magnetic interaction, exchanges of material, multiple satellite systems, and more complex streams of particles. To determine which possibility is real, scientists must separate the light of each component, monitor the signal across many rotations, and observe the system's motion for years. Only then can the source of the glowing methane be identified. If the signal changes with rotation, the explanation may lie in an auroral region. If it varies with the orbit of a moon, the particles may come from a small, unseen world. If it changes with the motion of the binary system, the two components may be influencing one another. And if the methane remains almost unchanged, energy from deep within the atmosphere may be playing the dominant role. Each hypothesis predicts a different rhythm of variation, and time itself will help separate them. The discovery of the binary system is therefore not the end of the mystery. It is a turning point that transforms the investigation from a solitary point of light into a system with multiple components, multiple sources of energy, and many more possibilities. W1935 still has no host star like the Sunday, but it is no longer a solitary world drifting entirely alone through the darkness. Each hypothesis would cause the system's light to change in a different way. Those changes may ultimately guide scientists toward the final answer. Science does not end with the words, "We do not know." When a signal cannot yet be explained, the next question is always what must be observed to determine which hypothesis is correct and which should be rejected. For this cold brown dwarf system, the answer will not come from a single measurement, but from many kinds of data assembled over time. The first task is to identify which object in the system is producing the methane emission. The initial observations collected light from both components at once, blending their signals together. Without knowing where the emission originates, every model of temperature, gravity, and atmospheric structure could be based on the wrong object. If the signal comes only from the larger component, the current models can be refined using its temperature and mass. But if the source lies within the smaller, colder object, the story will change considerably. A colder world that still creates a warm atmospheric layer would require a more powerful energy source or an entirely different mechanism. It is also possible that both components contribute to the spectrum. One may produce ordinary methane absorption, while the other creates emission. When the two signals blend together, they may form a complex pattern that no single atmosphere can fully explain. To separate their light, James Webb must observe the system at the appropriate infrared wavelengths. Each object may appear brighter at one wavelength and fainter at another. Only when the contrast becomes strong enough will scientists be able to read the signature of each atmosphere separately. Once the source has been identified, the next step will be to monitor it continuously for many hours. Brown dwarfs often rotate rapidly, sometimes completing a full turn in only a few hours. If the glowing methane is concentrated in a fixed location, the signal should change as the object rotates. A hot region can be imagined as a lighthouse on the surface of a dark sphere. When it turns toward Earth, the amount of infrared light increases. As it moves onto the hidden side, the signal weakens before returning during the next rotation. A regularly repeating cycle would show that the emitting region does not cover the entire atmosphere. It may be concentrated around a magnetic pole, a vast storm, or an area where energy from deep within is escaping upward. The rhythm of the signal would help reveal the rotation rate and the relative position of the hot region. If the methane emission changes dramatically during each rotation, the source may occupy only a small part of the atmosphere. If the variation is weaker, the warm region may be broader, or several areas may be glowing at once. If the methane remains nearly stable, the energy may be distributed across a much larger region. Stability does not mean the atmosphere is completely still. Many small hot regions could be spread around the object and balance one another as it rotates. Scientists must therefore monitor several wavelengths to determine whether methane, water vapor, and other molecules change together. If methane varies while the other molecules remain stable, the energy source may affect only a particular atmospheric layer. If the entire spectrum changes at once, clouds, temperature shifts, or a vast weather system may be altering the light emerging from many different altitudes. Another important test is the search for radio waves. Many brown dwarfs with powerful magnetic fields produce radio pulses that repeat with rotation. These signals are generated when charged particles move through a magnetic field and release energy at radio frequencies. If the system being studied also produces such pulses, the case for a strong magnetic field would become more convincing. This would not directly prove that auroras are causing the methane emission, but it would confirm that the magnetic machinery required for the phenomenon truly exists. The most important step would be to compare the timing of the two signals. If the radio emission strengthens at the same moment the methane glows more brightly, both may originate from the same magnetic region. An auroral zone rotating into view could produce a radio pulse while also heating the atmosphere. Even if the two signals repeat on the same cycle but reach their peaks at slightly different times, the difference would still be meaningful. The radio beam may point in a different direction from the brightest methane region, so the two signals would not necessarily reach their maximum intensity simultaneously. That offset could help reconstruct the shape of the magnetic field. Conversely, if radio waves are detected, but the methane does not vary with the same rhythm, the magnetic field may exist without being the primary source of heat. Auroral activity might then contribute only a small amount, while energy from within the atmosphere plays the larger role. If no radio waves are detected, the auroral hypothesis still cannot be ruled out. The signal may be too weak, absorbed before escaping, or emitted in a beam that never sweeps across Earth. Radio silence would therefore be only one piece of evidence, not a final conclusion. James Webb must also observe other infrared regions beyond the methane band that first drew attention. A complex atmosphere cannot be understood through a single molecule. Water vapor, ammonia, carbon monoxide, and carbon dioxide can all reveal how temperature changes across different layers. Each molecule is most visible at a particular altitude. By combining their signatures, scientists can reconstruct the atmosphere in depth. They may determine whether the warm region lies very high above, in the middle atmosphere, or deeper down where the pressure has already risen sharply. If only molecules in the upper atmosphere are emitting light, energy may be entering from space. If substances in deeper layers also change, heat may be rising from within. The vertical distribution is crucial for distinguishing auroras from atmospheric waves or convection. New chemical products may also appear when energetic particles plunge downward. Powerful collisions break molecules apart and allow their fragments to form other compounds. Although these signals may be extremely weak, they could leave a distinctive fingerprint of auroral activity. If those products are not detected, the absence would still not completely disprove the idea. In a dense, hot atmosphere, many molecules may survive only briefly before reacting again. Their signatures could disappear before the light escapes into space. Clouds are another factor that must be monitored. A thick cloud layer may hide the deeper atmosphere, weakening certain signals or causing them to change with rotation. If the methane appears brighter whenever the clouds thin, the phenomenon may involve a clearer view into a warmer region below. On the other hand, if the methane emission does not depend on cloud thickness, the energy source may lie above the main cloud layers. In that case, auroral activity or heating in the upper atmosphere would become a more suitable explanation. Tracking the motion of the two components will also be important. As they orbit one another, their relative positions will change slowly over the years. From that orbit, scientists can estimate their masses more accurately and determine the strength of gravity on each object. Mass directly affects atmospheric structure. A heavier object holds its gas more tightly, creating greater pressure and potentially allowing energetic particles to penetrate deeper before stopping. This determines where auroral energy is released and which molecules are able to glow. Once the masses are known, scientists can also estimate the age of the system. Brown dwarfs cool gradually over time, so their present temperatures are meaningful only when considered alongside their masses. A young object may retain much more internal heat than an older object with the same apparent temperature. If the system is young, its internal energy may be strong enough to generate atmospheric waves and heat the upper layers. If it is old, the weaker internal heat would make magnetic interactions or material supplied by a moon more important. Orbital motion may also reveal whether the two components are influencing one another. If the methane signal changes as their distance or relative positions shift, a connection with the binary system would become more significant. The emission may strengthen when the two magnetic regions enter a more favorable configuration. However, the orbital period may last for decades. Scientists cannot wait for a complete revolution before beginning their analysis. By tracking subtle changes in position and emission strength from year to year, researchers may already begin to identify the first meaningful trends. If the methane signal changes rapidly over only a few hours, the cause is unlikely to be the orbit of the binary system. Rotation, weather, or localized auroral activity would then become more plausible explanations. Each timescale of variation points toward a different group of mechanisms. Changes occurring over several hours are usually associated with rotation. Variations, lasting days or weeks, may be connected to weather or a nearby moon. Fluctuations unfolding over many years could reflect the orbit of the two components or gradual changes in the surrounding environment. These rhythms in time will help separate hypotheses that currently overlap. A signal that repeats regularly points to a stable mechanism. If the emission appears unpredictably, storms, eruptions of material, or the rearrangement of magnetic fields may be involved. Scientists also need to observe more brown dwarfs with similar temperatures. A phenomenon found in only one object may be regarded as an unusual exception. But if glowing methane is detected on many other cold worlds, it may prove to be a common feature of brown dwarf atmospheres. With more objects available for comparison, researchers can look for the conditions that tend to accompany the phenomenon. Does it appear more often on rapidly rotating objects? Is it associated with strong magnetic fields, binary systems, or younger brown dwarfs? If every object with methane emission also produces radio waves, auroral activity would become a very strong explanation. If none show evidence of magnetism but all display violent weather, internal energy would deserve greater attention. Broader comparisons would also prevent scientists from building an entire theory around a single case. One exception might result from measurement error, viewing angle, or a rare set of conditions. Several similar cases would reveal that a more general pattern is at work. New data may also eliminate some hypotheses. If the methane does not vary with rotation, the possibility of a small auroral region would become less convincing. If repeated observations from different viewing geometries reveal no radio signal at all, the magnetic field may not be as powerful as expected. If the orbit shows that the two components are too widely separated for their magnetic fields to interact, energy supplied by the binary system would become less plausible. If there is no evidence of a moon or escaping material, the idea of a local plasma source would also need to be reconsidered. On the other hand, a single matching discovery could transform the entire picture. A repeating radio pulse synchronized with the methane cycle would connect the atmosphere directly to the magnetic field. The discovery of a small orbiting body could provide the source of material required for auroral activity. A new chemical feature in the spectrum might reveal energetic particles colliding deep within the atmosphere. A cycle of variation lasting many years could demonstrate that the two components are influencing one another. Every measurement has the potential to remove another layer of darkness surrounding the mystery. The important point is that none of these tests has yet produced a final conclusion. They are pathways for investigation, not completed evidence. Science moves forward by requiring every hypothesis to make specific predictions and by accepting its rejection when the data do not agree. The mystery of this system does not lie in the discovery of a rare molecule. Methane can naturally exist in cold, hydrogen-rich atmospheres. If it merely absorbed light in the ordinary way, the result would not have raised such profound questions. What remains unexplained is how an object receiving no light from a host star can still create a warm layer high in its atmosphere. A source of energy is operating there, but it does not appear as a flame or as a bright point that can be seen directly. That energy may be heat carried upward from the deep interior. It may come from charged particles plunging along magnetic field lines, or the two components of the system, perhaps together with a small undiscovered moon, may be supplying material to an invisible auroral engine. Every possible explanation would require us to expand our understanding of worlds that lie between stars and planets. They are not merely failed stars slowly cooling away. Their atmospheres may contain clouds, winds, storms, magnetic fields, and intricate flows of energy. A world without a sun can still remain intensely active. Darkness does not mean silence, and the inability to shine like a star does not mean that everything within has stopped moving. The methane here does not prove the existence of life. It reveals only that an atmospheric layer is receiving energy through a mechanism that has not yet been fully explained. Yet this subtle trace has opened a new doorway into the study of auroras and weather on some of the coldest celestial objects known. The final answer may not belong to a single mechanism. Internal energy could warm the atmosphere across a broad region, while auroras add further heat near the poles. A companion object or small moon may provide the necessary supply of particles. Science can discover the truth only by continuing to observe. Separating the light of each component, monitoring the methane across many rotations, searching for radio waves, and measuring the orbital motion will gradually reveal the machinery operating within the darkness. This cold world may contain no life, but it is showing us that an object without a sun can still possess a dynamic atmosphere, heated and transformed by mechanisms that humanity is only beginning to recognize. Let us return to that tiny point of light in the constellation Sagittarius, about 47 light-years from Earth. From such a distance, James Webb cannot see a clearly defined surface, photograph individual clouds, or capture a brilliant ring of auroral light like those humans observe on Earth. The telescope collected only an extremely faint amount of infrared light that had traveled through space for nearly half a century. That light was separated into many smaller parts, and within the wavelengths associated with methane, an unusual detail appeared. Instead of merely absorbing energy, the molecule seemed to be emitting light back into space. It was a very subtle trace, yet enough to raise a profound question. Some part of the atmosphere is receiving additional energy, even though no bright sun-like star exists nearby. This mismatch between observation and prediction transformed a faint brown dwarf into one of the most intriguing worlds of its kind. Methane is often described as a gas of life because, on Earth, most of it is connected either directly or indirectly to living organisms. But throughout the universe, the same molecule can form through many different pathways. Rock, heat, water, and chemical reactions can also produce methane without the presence of a single living cell. A molecule, therefore, can never tell the entire story on its own. Its meaning depends on where it appears, the temperature of its environment, the composition of the atmosphere, and the energy sources surrounding it. Methane on a temperate rocky planet cannot be interpreted in the same way as methane within the hot, dense, hydrogen-rich atmosphere of a brown dwarf. This discovery is not evidence of extraterrestrial life. There is no indication that living organisms exist there or are producing the methane. The true mystery lies not in the origin of the molecule, but in the unusual condition of the atmospheric layer containing it. The question is not what is creating the methane. The question is what is making it glow. Energy may be rising from the deep interior. The object still retains heat from its formation, while its atmosphere may contain powerful winds, enormous storms, and waves that carry energy upward. As these motions dissipate, some of their energy may be converted into heat. The answer may also lie in a magnetic field. Charged particles captured and guided into the upper atmosphere could produce a form of aurora almost entirely invisible to human eyes. Instead of glowing curtains of green and red, the phenomenon may reveal itself only through heat and infrared light. But an aurora requires a source of particles. On Earth, those particles come from the Sunday around Jupiter. The moon Io continuously supplies material to the planet's magnetic environment. In this cold system, however, the source of the plasma remains uncertain. A small, undiscovered moon may be releasing gas or dust into space. It would not need to be large or bright, only active enough over time to provide material for the magnetic field. From nearly half a century of light travel away, such a small world could easily disappear within the glow of the larger object. New observations have also shown that the original point of light is not completely alone. It contains two cold components orbiting one another within a system that has no luminous host star. This discovery introduces the possibility of magnetic interactions, exchanges of material, or even smaller moons still hidden in the darkness. Yet the binary system also makes the story more complicated. The initial observations did not establish with certainty which component was producing the methane emission. The signal may belong to the larger object, the colder companion, or result from the blended light of both. To find the answer, scientists must separate the light of each component. They need to monitor the methane across many rotations, search for radio pulses, and observe how the signal changes over time. Each rhythm of variation may point toward a different source of energy. If the light rises and falls over a period of several hours, the emitting region may rotate with one of the objects and be concentrated near a magnetic pole. If the signal changes slowly with the orbit, the two components may be interacting. If the methane remains nearly stable, energy rising from deep within the atmosphere may play the greater role. At present, no hypothesis has enough evidence to become the final explanation. Auroras are consistent with some of the clues, but still lack independent confirmation. Internal energy may contribute to the atmospheric heating, though it is not yet clear whether it is powerful enough to produce the entire signal that has been observed. This uncertainty is not a weakness of the discovery. It is how science moves forward. A new observation does not always provide an immediate answer. Sometimes its greatest value lies in revealing where existing models can no longer fully explain nature. This world matters, not because methane is a rare molecule, but because a familiar substance is behaving in an unfamiliar way. An atmospheric layer that should be colder is instead being heated, while the source of that energy remains absent from every image. The discovery forces scientists to expand their understanding of auroras, magnetic fields, and atmospheres on objects that exist between stars and planets. Worlds without a sun may be far from silent. They may still contain clouds, winds, storms, electrical currents, and intricate mechanisms for transporting energy. Darkness does not mean that all activity has ended. An object that cannot shine like a star may still possess a dynamic atmosphere. Even without receiving light from outside, it can generate heat, magnetic fields, and phenomena that humanity is only beginning to recognize. In the darkness 47 light-years away, that cold world continues to cool, just as it has for billions of years. Yet somewhere above its invisible clouds, methane is still releasing light. Until the source of the energy illuminating it is finally found, that distant place will continue to hold its secret.